Thumbs up. Okay. Well, welcome to Brookings, and thank you very much for being here. I'm Adam Looney. I'm the director of the Center on Regulation and Markets here at Brookings. We're very excited to bring you today's events in collaboration with Texas A&M and the University of Florida. We'll be gathered here today for most of the duration of the day. I wanted to remind you that today's event is being live streamed, and so there are people joining us from their homes and offices. You should all have a hard copy that describes today's program and the bios of all the participants. I just wanted to emphasize that there are two panels this morning, there are two panels this afternoon, there are two featured speakers, and in between I wanted to encourage you to join us for lunch at the conclusion of the first two morning panels, and then for a reception that begins immediately after the last panel. And I wanted to begin this program with another introduction, which is an introduction for our co-hosts from the University of Florida and Texas A&M. Dr. Lily Eleftheriadou, the director of the University of Florida Transportation Institute and the Barbara Goldsby Professor of Civil and Coastal Engineering, and Dr. Karoke Ray, who is the director of the Mays Innovation Research Center at Texas A&M and a professor of accounting at the Mays Business School. Do you want to say a few words of introduction? Okay, well then come on up, and thank you all for being here.
Good morning, everyone. On behalf of the University of Florida Transportation Institute, I want to welcome you to this very exciting workshop, Autonomous Vehicles, which is going to focus on technology, science, and policy. As you know, this is a very exciting time in transportation, and we have been partnering with industry, with academia, with the public sector, to develop and deploy advanced transportation technologies. Florida is one of the largest states, the third largest in the US, and has been for many years a pioneer in transportation infrastructure. And of course, no surprise, they're now at the forefront of deploying advanced transportation technologies. So looking forward to the discussions today and the panels, and I want to thank our collaborators, Karoke and Adam, for putting together this event. I also want to thank Anna for organizing the event. Thank you. Welcome.
Howdy. It's great to be here. Thank you for everyone for coming. This is an exciting time for all of us. I feel like it was just yesterday when a few years ago I was in my office coding in Python to gather some data for my research in economics. And about an hour later, I was on an abandoned airfield at Texas A&M with Shiva, and he was in the back seat with me, also coding in Python to navigate an autonomous vehicle. It really showed me how technology has truly penetrated our lives. And in this conference, I hope we can talk about the technology and also understand all the opportunity it can bring. So thank you all for coming. I want to especially give a shout out to John Canavo and Anna Dawson, who did an excellent job coordinating this. We couldn't have done that without them. And we really look forward to all the exciting discussions today. I believe this is going to be a little bit of a mix where we'll have science in the morning and policy in the afternoon. I spent a decade of my life in DC, and I always felt like there could be more science to some of the conversations. So this is our first attempt at that. So I hope you enjoy the experiment, and I look forward to meeting everybody later today.
I don't know if I could pull off a howdy in the same way. Welcome, Texas. Well, it's my pleasure to welcome our first speaker, Ken Leonard. Mr. Leonard is the director of the U.S. Department of Transportation Intelligent Transportation Systems Joint Program Office. He spent more than 30 years in federal government and in the private sector, including at the Federal Motor Carrier Safety Administration and the Federal Aviation Administration. He's a recognized leader in the field of intelligent transportation systems, and he brings a unique perspective to what has to be accomplished to do research, develop capabilities, and implement successful intelligent transportation strategies. I'm very excited that he's here to open our program, and so please join me in welcoming Mr. Leonard.
Well, good morning. Good morning. I am Ken Leonard. I'm the director of the Intelligent Transportation Systems Joint Program Office. And for nearly 7 years, I've had the great pleasure to work on an exciting portfolio, including some of the most fascinating topics in transportation science, technology, and policy. The JPO Vantage Point allows us to look at intelligent transportation issues through a broader multimodal lens. I'd like to start by thanking the Brookings Institution, Texas A&M, and the University of Florida for sponsoring this event. I'm honored to speak on a topic that's at the top of USDOT's innovation agenda. The USDOT has worked to develop the tremendous promise of connected and automated vehicles to solve some of transportation's toughest challenges, to reduce or eliminate the 6 million crashes, 3 million with injury, and almost 40,000 fatalities on the nation's roads each year. We partner with a broad coalition of industry, academics, federal, state, and local agencies, safety advocacy groups, and others to support safe development, testing, and deployment of intelligent transportation technologies. We're working together to bring connectivity to our roads, to create a connected transportation ecosystem in which our cars, our infrastructure, and our mobile devices communicate to yield quantifiable safety benefits and an improved system efficiencies. Why? Because connectivity is a problem worth solving. Connected vehicle technologies have tremendous potential to reduce congestion, expand our individual mobility, maximize system efficiency, all to improve the quality of our lives, and most importantly, to save lives. Innovation, and specifically ITS innovation, has the power to transform our lives. We're on the cusp of monumental changes. We see the maturing of past research in connected vehicles as they move from demonstration to marketplace, and as we see a new wave of emerging technologies such as automated vehicles, artificial intelligence, robotics, fueled by the power of connectivity, data, advanced analytics, and machine learning. We believe in the power of demonstrations and early deployments of technologies to identify and overcome barriers to realizing ITS technology's full potential. Our demonstrations reduce risk and pave the way for widespread adoption. 3 of our largest connected vehicle pilot deployments in New York City, Tampa, Florida, and across the state of Wyoming are implementing applications tailored to meet each of those regions' unique needs. The 3 locations are bringing together more than 10,000 connected light vehicles, trucks, traffic signals, and pedestrian devices to their communities. Our pilots successfully demonstrated site-to-site equipment and application interoperability to show that they can operate as designed anywhere in the country, regardless of which competing manufacturers build them. In addition to interoperability, we've worked out some of the cybersecurity challenges. Since the inception of our connected vehicle program, we understood the potential vulnerability of information sharing among vehicles, and we incorporated the concepts of privacy and security by design from the outset of the development of our communications protocols for DSRC on 5.9. This is a critical design concept that is overlooked at great peril in the rush to utilize spectrum for transportation purposes. We also funded the development of a security credential management system, or SCMS, proof of concept demonstration, which secured vehicle-to-vehicle and vehicle-to-infrastructure communications. This system is now available via the commercial marketplace to support deployment. In fact, the U.S. has over 80 ongoing and planned deployments of connected vehicles. We know vehicle communications must be effective, affordable, ubiquitous, and interoperable to meet transportation's goals. As communities begin to deploy connected vehicles, DOT remains committed to protecting the 5.9 gigahertz spectrum for transportation communications essential to public safety today and in the future. Connected vehicles are just one example of our research and investment in an advanced automated transportation ecosystem to improve the quality of life for everyone and to achieve our vision to transform the way society moves. We're making progress not only in connected vehicles, but in automation as well. In 3 successive years, from 2016, 17, and 18, we released substantive policy documentation on automation. Our Federal Automated Vehicle Policy Guidance document explored big picture questions around automated vehicles, such as legislative authorities, certification issues, and impacts. Our Federal Automated Vehicle Policy Guidance document, our Federal Automated Vehicle Policy 2.0 clarified the voluntary self-assessment process and emphasized motor vehicle safety. The number of firms submitting self-assessments has grown to 17, and it's a number that changes almost week to week. And while we've always remained committed to motor vehicle safety, we have expanded our discussion of a more robust and multimodal approach. And then released in 2018, AV 3.0 advances DOT's commitment to supporting the safe integration of automation into the broad multimodal surface transportation system. It reiterates approaches to safety that were established in prior guidance, provides new multimodal safety guidance, and outlines a process of working with the department as the new technologies evolve. Preparing for the Future of Transportation, Automated Vehicles 3.0 establishes a clear federal approach to sharing policy for automated vehicles, or for shaping policy for automated vehicles based on the following 6 principles. First, we will always prioritize safety. U.S. DOT will lead efforts to address potential safety risks and advance the life-saving potential of automation and seek to strengthen public confidence in these emerging technologies. We will remain technology neutral, adopting flexible technology policies to promote competition and innovation and achieve safety, mobility, and economic goals. We will modernize regulations. U.S. DOT will modernize or eliminate outdated regulations that unnecessarily impede the development of automated vehicles and that do not address critical safety needs. Fourth, we will encourage consistent regulatory and operational environments. DOT will build consensus among state and local transportation agencies and industry stakeholders on voluntary technical standards and advance policies to support the integration of automated vehicles throughout the transportation system. And we will proactively prepare for automation. We'll provide guidance, best practices, pilot programs, and other assistance to help our partners plan and invest. But we won't assume universal implementation of any particular approach. And finally, we'll work to protect and enhance the freedoms enjoyed by Americans today. We embrace the freedom of the open road, and we envision automated vehicles operating alongside conventional, manually driven vehicles and other road users. These 3 policy documents are just the tip of the iceberg, and we've taken many steps to advance the science and technology of connected and automated vehicles with our research and deployment funding and convening activities and events. And I'd like to share about a dozen of these activities with you. In 2017, we hosted a roundtable on data for automated vehicle safety to explore voluntary data exchanges to accelerate the safe deployment of automated vehicles. As a result of that roundtable, we've created a minimum viable product for automated vehicle work zone data exchange with a number of states, and multi-state pilots are anticipated soon. We hosted over 1,000 stakeholders at a public listening session summit on automated vehicle policy in March of 2018 to seek input and broadly engage the public. U.S. DOT modes have published requests for information from stakeholders, and we've analyzed thousands of comments that we've received. Several modes have engaged with their stakeholders through face-to-face national dialogues and public listening sessions, some just as recently as last week at AVS in Florida. And we're assessing national issues, developing technical guidance, supporting research, adopting programs, policies, and creating a national community around automation. One of our most important partners in solving automation issues is Congress. And in response to the Omnibus 2018 Appropriations Act, we developed a plan that communicated our management and research demonstration plans, as well as coordinated across the department on over $100 million in additional funding going into automation. As part of the Omnibus in December of 18, the department published a NOFO, a Notice of Funding Opportunity for ADS demonstration grants. These grants will provide up to $60 million in funding for projects that test the safe integration of ADS on our nation's roadways. We received a lot of interest in the grant funding opportunity, and the application closed in March. We expect to announce awardees soon. We're also partnering with the Department of Labor, the Department of Commerce, and the Department of Health and Human Services to conduct a comprehensive analysis of workforce impacts and operational safety issues for commercial drivers that are introduced through automation technology. We held an event in March to gather stakeholder input, and we're in the process of developing a study and will publish a report this summer. Our goal is to provide information to policymakers and the public to help the nation prepare so that we can all benefit from the introduction of new technologies such as automated trucks. NHTSA, FMCSA have issued advance notices of proposed rulemakings on the removal of unnecessary regulatory barriers to the safe introduction of ADS vehicles in the United States. Both agencies are seeking comments at this stage to ensure that all potential approaches are fully considered. As the agencies move forward with these regulatory actions, we encourage you to submit comments to the Federal Register dockets. Comments on both ANPRMs are due July 29th, so just around the corner. The Department has also sought public comment on proposed exemptions to federal standards and how the public can be protected as new transportation technologies emerge. In March, NHTSA issued 2 requests for comment in response to petitions for the temporary exemption of the Federal Motor Vehicle Safety Standards, FMVSSs, submitted by General Motors and Neuro, respectively. The comment periods closed in May, and NHTSA is reviewing the comments that they've received. Federal Highways has developed the KARMA platform to encourage collaboration between transportation systems management and operation strategies and automated driving technology, focused on how infrastructure can move traffic more efficiently. And 3 awards were made for truck platooning projects to assess in-service truck platoons delivering commercial goods via fleet operators on their common delivery routes to understand how truck platoons will operate in a realistic operational environment. Results will inform state and local decision makers that develop truck platooning regulations. And lastly, but certainly not least important, in April and June of this year, we held 2 public sessions on the 5.9 gigahertz safety band. The safety band is critical to ensuring connectivity that enables cooperation through secure, uninterrupted, low latency, interoperable, proven communications. Protecting the 5.9 gigahertz band of radio spectrum, the safety band, is of critical importance to the department. It's uniquely capable of supporting safety applications that prevents or significantly reduces the severity of vehicle crashes in a manner that's not available through existing vehicle technologies. The safety band is already used by state and local transportation departments for vehicle-to-vehicle, pedestrian collision avoidance, as well as emergency vehicle priority. The safety band also enables applications for red light warnings, reduced speed warnings, curve speed warnings, spot weather impact warnings, and other safety-critical applications. As technology advances, interoperability remains central to enabling universal vehicle-to-everything capability and benefits. USDOT must ensure that the safety band is protected for traffic safety. The department is technology neutral, but we're not technology agnostic. We believe that technology must perform. It must deliver on the promise of safety. Safety is our highest priority, and transportation technology using the 5.9 safety band must demonstrably achieve it. At the same time, we encourage the automotive industry, wireless technology companies, and other innovators to continue developing multiple technologies that leverage the 5.9 gigahertz band of spectrum for transportation safety benefits. So as you can see, we've been pretty busy. USDOT is moving forward with both connected and automated vehicles. We're committed to engaging stakeholders to identify and solve scientific, technical, and policy issues and usher in a new era of transportation. The department will work with partners to integrate connectivity and automation across the transportation system, enhancing mobility for seniors, people with disabilities, facilitating freight movement, and increasing productivity. The DOT's actions represent just a step in the right direction. We know that it's a long road, but one that we must take together. Connected vehicle technology is proven and in deployment. Despite its promise and the progress that's been made, automated vehicle technology is still in its early stages of development. The public has concerns about the safety and security of this new technology. These concerns must be addressed because without public acceptance, we know automated technology will never reach its full potential. Ensuring that we establish common methods to evaluate the safe performance of emerging ADS-equipped vehicle technologies is critical. DOT and industry are working to assure the safety of ADS-equipped vehicles. The department supports automation in a safe and secure environment where innovation can thrive and the American public can be excited and confident about the future of transportation. The promise and safety of automated vehicles is only possible if we all work together. So in conclusion, and in advance of your discussions today, let me thank you again for your work to advance smart transportation. So thank you.
Good morning again. This first panel will focus on the technical and scientific aspects of autonomous and connected vehicle technologies. First, I'll start with an overview of those technologies and their deployment. My background, just to give you an idea, is on traffic engineering, my expertise in traffic flow theory, and civil engineering. Dr. Carl Crane is a professor of mechanical engineering at UF. He's been working on autonomous vehicles for several decades. He's developed both surface and water vehicles, autonomous vehicles, and he'll discuss the technology and sensors for autonomous vehicles along with the deployment challenges. Next, Dr. Shailene Klassen is a professor and chair of occupational therapy, and she's an expert on fitness to drive issues and driving simulators, and she'll discuss the interactions of technologies with humans, and particularly perceptions by older drivers. Dr. Sanjay Ranka is a professor of computer and information sciences and engineering. He's an expert in parallel computing and machine learning, and he'll discuss transportation-related data management applications that are underway. First, let's start with the status of the transportation system in the U.S. And Ken mentioned the more than 40,000 fatalities in the U.S. This past year. This graph shows how the number of fatalities have changed since 1975, along with the fatality rate per 100 million VMT. As you can see, both numbers have been going down, and even though vehicles and the infrastructure have generally become safer, the vast majority of these crashes, 94%, are due to human error. So the promise of autonomy is to reduce these substantially or even eliminate them. You have seen various tests by Google, Uber in the news, and now there are more than 1,400 vehicles being tested by more than 80 companies across the US. We see more and more shuttles, such as the one shown here on the screen, which is the one in Gainesville. And I'm going to play a little video here. So as you can see, the vehicle is going really slowly. It's really frustrating if you're behind it, but it is because it's mapping the route. And during that time, I don't know if you caught that, but there was a bicyclist zooming by, and the vehicle just stopped. Wouldn't it be nice if all our vehicles could do that? And this, by the way, was not staged. This is something that just happened while the vehicle was mapping the route. This shuttle is going to be part of the regional transit service in Gainesville. We're waiting for approval from NHTSA. The vehicles themselves are in Gainesville. But we hope this will give us great information about interactions with the public how people might use autonomous shuttles. Now, let me take you back to when vehicles were first invented. That's what they looked like. So we didn't get to where we are overnight. It took about more than 100 years to get to the transportation system of today. And at that time, acceptance of vehicles was very far from universal. There was significant congestion, significant safety issues, no rules of the road, no stop signs, no traffic lights. And at the time, of course, horses were prevalent with problems, manure, mistreatment of the animals, and so on. So mixing the two was a challenge. The horses were getting scared of the cars. So this little invention was introduced. It's a horse head so that horses wouldn't be spooked. Of course, that didn't work. But in some ways, we face similar issues today with humans accepting autonomy. How will conventional vehicles and drivers operate around autonomous vehicles? Will they cut them off because they can trust that an autonomous vehicle will stop? How will the autonomous vehicle interact with pedestrians and bicycles and scooters, which are very prevalent on the UF campus? So the concept on this slide is kind of similar to the horse head. Now we want to make the vehicle look and act like a human driver, so that pedestrians and other human drivers can understand what the intent of the vehicle is. So if the vehicle is approaching, are they going to stop for me to cross if I'm a pedestrian? And the autonomous vehicle logic also wants to know, is the pedestrian standing on the side of the road getting ready to cross, or are they just waiting for something else? So in my field, in traffic engineering, we use this graph in introductory transportation engineering courses. And it shows the three major elements of the transportation system: the vehicle and its characteristics, the driver, the traveler, and then the infrastructure and the environment. So each of these affects and is affected by the other elements, and altogether contribute to the performance of the transportation system. So the speeds that we observe are a product of all these. The capacities are a product of all these. So as an example, when you have a heavy truck, it's traveling much slower when you have a steep upgrade. So the combination of the vehicle characteristics and the infrastructure result in a particular performance. Each of us as humans, we react differently to the different designs. Some of us are more conscious, some are more aggressive, some we want to keep longer distances, shorter distances. So this variation that we have from human drivers also affect the speeds, the travel times, and the safety. So how do the EVs fit within this system? How will different travelers use and interact with AVs, with autonomous vehicles? How will different vehicles from different manufacturers operate under different highway designs? So when we're introducing autonomous vehicles, we have to consider all three elements. We have to consider the variabilities in driver behavior, both in using a particular autonomous vehicle and driving, as well as interacting with it as a pedestrian or as a bicyclist. So here's a graphic that is of this type is commonly used to describe autonomous vehicle operation. So an autonomous vehicle maps the terrain. It has several types of sensors by which they're able to look at obstacles and navigate through the highway network. Now, once these are detected with the vehicle sensors, then the vehicle's logic decides how it's going to move, whether to stop, and whether to change lanes. But imagine this scenario on this slide where you have an autonomous vehicle which approaches a crosswalk, and there's a pedestrian already on the crosswalk. There's a bicyclist further ahead, and this can be seen by the sensors. But there's another pedestrian standing there, and its view may be somewhat obstructed by the sensors on the vehicle. So can the vehicle detect the pedestrian, first of all? And even if it can detect it, can they determine the intent, whether the pedestrian is getting ready to cross? When we have a human driver, the human driver can communicate that nonverbal with the pedestrian, determine the intent, allow them to motion them to pass, and so on. And this becomes a very difficult problem, especially considering the variability in driver behavior. So different individuals will behave very differently. Now imagine this environment, freeway congestion, and an autonomous vehicle operating in it. In this environment, you'd have very frequent lane changing as vehicles are trying to get to the correct lane for their destination. And so when you have an autonomous vehicle under this environment, the autonomous vehicle has to recognize the intent of other vehicles changing lanes. Second, you have a distance that an autonomous vehicle needs to keep with a vehicle ahead to maximize its safety. If that distance becomes too long, then the space that this queue occupies with conventional vehicles becomes much longer. If it's too short, it may cause rear-end crashes. So the vast majority of autonomous vehicle crashes that have been recorded so far are due to human error of a conventional vehicle crashing into an autonomous vehicle because they don't react quickly enough. The human driver doesn't react as quickly as the autonomous vehicle. So autonomous vehicles do have the potential to significantly improve safety and mobility, but there are risks in their deployment. And those deployments may be derailed if we start increasing delays and crashes. So the wrong type of deployment, when the technology is not ready or well thought out, will backfire. Let me show you now an example of how we're approaching this problem to avoid these pitfalls for deployment of autonomous connected vehicles. We have a partnership at the University of Florida with the Florida Department of Transportation and the city of Gainesville to build the iStreet, which is a real-world test bed. And its objective is to test, deploy, evaluate several different advanced transportation technologies. Gainesville and the UF campus where this is deployed are ideal for this type of testing because there's significant pedestrian, bicyclist traffic, there's scooters. We have an extensive transit network. We have relatively low speeds and good weather. Also, Florida is very welcoming to autonomous and connected vehicles. So the Florida Department of Transportation has funded the deployment of communication devices for connectivity along several corridors, including corridors around the UF campus. And those allow vehicles that are instrumented to communicate with infrastructure. So what I'm showing in this slide is a system we're developing for optimizing signal control, so the operations of traffic lights, and the way that the green is allocated to the traffic approaching the intersection, while at the same time advising arriving vehicles that are able to receive this information what their optimal path is or their trajectory. So the autonomous vehicles approaching the intersection, as soon as they reach the communication range, they receive very specific information on the path that they should follow, and they can execute it. We've been doing experiments now for a couple of years, and we've developed the hardware and software to be able to to do this. With connected vehicles, which are also part of the mix, if they have the ability for connectivity, then they can also receive information on optimal speeds. And right now we're working on an app where we are able to have even conventional vehicles with no connectivity be able to receive information on optimal paths, advisory speeds in essence. This video shows how we use radar and other sensors. This is at an intersection on the UF campus, Stadium Road in Gay Lemerant. You see our football stadium there on the left. So that intersection is instrumented so that when the vehicle is connected, it can receive an optimal path, which is the green points there. So when we first detect a conventional vehicle, we estimate its projected path, we optimize signal control, and then as the vehicle moves, we reevaluate that path and adjust the signalization if the vehicle is slower or faster than what we predicted. So with initial simulation experiments for a fully autonomous simulation environment, but with communication with the infrastructure, our experiments show that we can reduce delay by 20 to 70% depending on the demand. Of course, that number goes down when you have mixed traffic and lower market penetrations. We start to see a significant difference when we get to about 20% market penetration. So a system like this cannot function if it doesn't have communication with the infrastructure. And to be able to take advantage of such systems, we have to have collaboration that involves the public sector and industry, academia. And so iStreet is approaching this as a collaboration with our partners, FDOT and the city of Gainesville. Because if we don't get this right, if we don't make a difference, then congestion will get worse and deployments for autonomous vehicles will backfire. So this map here on the right shows our ongoing deployments around Gainesville for iStreet. So I invite you to check out our work on iStreet. You'll hear some more with the next 3 presentations, and we look forward to working with you to improve mobility and safety. Thank you. And with that, I'm going to get Dr. Crane here for the next presentation.
Okay, well, thank you very much. Oh, we call her Dr. Lily. So she's a fantastic leader of our efforts down in Florida. So I was asked to try to do this. I'm watching that clock there. A 15-minute overview of autonomous vehicle technologies to a group of experts in a wide variety of topic areas, which is usually a recipe for disaster. So here goes. A little bit of the I'm glad you started with the old cars, and I hadn't seen the horse head. I thought that was great. Background, I've been in Florida a long time. I'd been in the Army before I got to Florida, and like in the Army, every 3 years you transfer, and so my 3 years got up, I was like ready to wear it, and I've been there now for like 35 years, so I guess it's not gonna happen. But over that time, we've done a lot of autonomous vehicle work for the Air Force, for different projects that they had. And then in the mid-2000s, DARPA had their Grand Challenges and the Urban Challenge. So I was going to say we participated in all three. The Urban Challenge, the Grand Challenge, if you're not familiar, was they gave along a desert route a bunch of latitude, longitude of a whole bunch of points, about a 150-mile long path. And whoever could do it the fastest would get $1 million, well, then they upped it to $2 million prize. And the first year, 5 vehicles got about 5 miles, and 5 got about 1 mile, and 5 self-destructed at the starting gate. And they were the best 15 out of 43. We were in the middle group. We got about 1 mile. my goal, make sure we get out of sight of the starting gate, and then whatever happens, happens. The second year, though, definitely it was about a year and a half later, they redid it. And again, 43 teams, they put 23 in the race. 5 completed, and the fastest was Stanford. And they got the $2 million prize and kind of led off to Google Waymo and all that. We got about 14 miles and our GPS went out. Well, our GPS, which is supposed to broadcast corrections of a few centimeter level accuracy, had an 8-meter error in GPS. And the entire vehicle was a single point failure vehicle. So I can't say that I was disappointed. That's not the right word. That was actually our high water mark, I think. And it was really exciting to see that happen. So now I've used up all that time on the first slide. What I want to do today is just show, sort of a basic overview of what's going on with autonomous vehicles. And I don't have to spend a lot of time on this chart. Is this the laser pointer? Yeah. But what really jumps at me is that orange word deaths. And when you see that, and it's next to that blue line, and it's going way up high, and you say, oh my goodness, this is terrible. But it turns out that's actually vehicles miles traveled. And one of the other increasing one is population. And if you go to the very bottom line about deaths per billions of vehicle miles traveled, there's been really improvements. And I think a lot of the safety factors that you had mentioned with I'm going to get a new car this fall, and I'm going to get everything I can on it because it's amazing what they've got out there. So there has been big improvements, but there can be better. So if I look at the basic problem for one autonomous vehicle, basically all you have is you have instantaneous sensor data and you have whatever a priori or map data that you have ahead of time. That's all you have. And from that, again, at every instant, you have to get your throttle, steering, braking, what do you want to get to come out of it. And for the instantaneous sensor data, one is localization. Can you get some idea, like a typical GPS might be, 4-meter accuracy, and that's not too bad. We can do better than that with some other technologies. Identify static objects, the terrain, where is it smooth, where are the curbs, and lane markings. But the moving objects are the big one, the other vehicles and pedestrians and things like that. How do we do it? And the main sensors that are out there, I think I just hit the accelerator pedal. I got to go a little faster. The main sensors that are out there, LiDAR is very popular. So you shoot the laser and you get a point cloud. You get this point data. And the advantage is 80 meters is easy. We've got one sensor that claims iSafe 300 meters that we used in I mentioned about the Urban Challenge. That's the City Street DARPA competition I forgot to talk about. But you might miss the target. The beams, it's not continuous. Reflections due to rain, things like that, or certain materials don't reflect the material, the beam that well. Vision is great because it's passive. You're not sending any signal out there. But again, lighting and weather conditions and something as simple as the stripe in the road going under a shadow of a tree can cause some issues sometimes. Ultrasonics, when we started way back with some of our Air Force work, we were moving very slow. It was construction equipment, and ultrasonics is the poor person's sensor. They are inexpensive, but short range, and all you know is that in this cone of area, there's something out there, but you're not sure where. And radar is probably one of the best as far as bad weather and things, so that you can get it out there. But again, it's not pinpoint, sort of like a laser beam as far as locating where something is out there. This is our Urban Challenge vehicle. So that was the competition DARPA did out at Air Force Base that was closed in Victorville, California. You had to drive on city streets. Again, there was a $2 million prize, but it was a bit more subjective this time. Instead of who did the 150 miles the fastest, it was clear who the winner is this time. So first place was Carnegie Mellon, got $2 million. Stanford got $1 million, second place. Virginia Tech third, got $500,000 prize. If I was to ride in one of the vehicles, maybe I shouldn't say which one I would want to ride in. This is our vehicle. It's a Toyota Highlander that we did. We have a lot of single beam lidars down at bumper level. You see the SICK, but it's a German sensor, pronounce it ZIC. I don't know. So it sends out a single beam. So on the bumper level, there's sort of a plane of beams that are out there. And if you look at this top-down view, there's an L shape right in the middle. It has a number 36 next to it. That's what, from the top view, that's another vehicle. So we've got to interpret that as a vehicle. Some of the other objects, you see how we've grouped them together anyway, are buildings and things, and the vehicle itself is that rectangle that's not labeled in the middle. And then as you move forward, this is some of the technology where the prices have come down now. This is a Velodyne 16-beam LiDAR that we use quite regularly. And you can see how it's angled on the left-hand picture so that it swings the 16 beams 360 degrees. On the left of the blue dot thing, all that mess up there are the trees, because it's the back side of the LiDAR is shooting up there. But on the right-hand side, you can see the 16 beams as they're sweeping across the road. So again, you don't get continuous total data, but you get all these points as indicated by those blue dots. This is the 16-beam LiDAR that we put on our vehicles. We're driving around campus. So again, you get a lot of information. And the problem becomes how to interpret that fast. And the 64-beam LiDARs are very popular. When these first came out, though, I think the 64 matched to the price. I think it was $64,000. Yeah. So, but you get a lot of data. And you say, well, why is that important? Well, we're going to get to that. I forgot this slide. What about the a priori information? Okay, I got 5 minutes. Right, we're going to have maps. So how are we going to represent those maps? Are they going to be point clouds? Or are they just going to be, well, let's show the options. This is the map that we had for the DARPA Urban Challenge. It was a text file. And if you look down the list here, you see about halfway down on the left, it says number of lanes 2. And then 2 lines below that, it says lane 1.1, number of waypoints 4. And down at the bottom of the left-hand column, you can see 4 pairs of numbers. Those are latitude, longitude of certain points. And then it says end of lane 1. And then in the right-hand column, lane 1.2, so it's segment 1, lane 2, has 6 waypoints, and you can see the lat long. And the third line in the right column, no, fifth line, it says exit 1.2.4 and then 3.1.1. That means that you can exit or you can transition from segment 1, lane 2.4 to segment 3, lane 1.1. So that was our world. That's all we had. And from that, then, we'd plan routes to, we were given a mission file, say go to points 8, 11, 20, in a certain order. So you had to plan your route with that information. So do you have a map like that, or do you give an entire point cloud? So this was us driving down one of the roadways in Gainesville with the 16-beam LiDAR on just one single pass, and you can even see the wires and the power lines. And it's a lot of information, but it's all available. Or do you take all that information and try to condense it down? So you can make a voxel representation, so it's sort of like Minecraft representation. So on the left, you see all these boxes. And on the right, we did some classification. This is something for the Air Force. We were looking for tree trunks and not people. And the purple we identified as tree trunks out of the one image. So if you have the instantaneous sensor data and you have some type of map data, how do you decide what to do? I'm not going to dwell on this slide, but one of the biggest things we did on our Urban Challenge vehicle was how do you decide what behavior to do? Again, it was to go from that sense data, which is the blue thing on the bottom, to throttle, braking, and I'm going to zoom through that one. Okay. What can you get today? And I have to apologize to some of the other vendors. This is a Tesla video, but General Motors has some great stuff. A lot of the people have great stuff. So if you go to the showroom today and buy something, you can basically be on like an interstate and do lane changes, stay in your lane, stay behind a vehicle. Summon is kind of cute, it tells it to pull out of the garage and come get ready to go. And, automatic parking is, it's been out there quite a while. And the last one is emergency braking. And those they're really good things. And I'd love to have that in my car, but it's not an autonomous car. So, again, trying to rush through in 15 minutes, then you go from what's available to buy today, go to some of the technical topics, maybe some of the things that keep us up at night. And I'm going to go back to the LiDAR. So, the problem with the LiDAR is how do I take, for example, this point cloud? So on the left are all the points that were hit. I believe there's 16 beams here. Somebody was about 2.5 meters away. You get a lot of data. And you can see on the right-hand side, you can hardly see the dots at 17 meters. And 17 meters isn't that far, that you don't get that many hits. So how do I identify that as a person? So this is from a TED Talk from Chris Urmson from Waymo. One of the approach was they generated all these not scenarios, but data of actual people and have stored them, and then you compare, the point cloud little bit that you have to the models you have and identify. And then this is one of, I just wanted to show a case. I don't want to say things that keep us up at night, but let's see if I can get this to play play. Okay, oh, it was playing. There's an intersection indicated by those orange lines, and the mouse was wiggling by a person there. And this is the raw data, and we've classified it now. There's the person, and the person's about to walk across the road. And you can see we're getting great point hits. The sensor is located at the intersection of the blue, green, red lines. And as they walk across the look at how it disappeared. Now, if you look at the raw data, there's still data there, but our algorithm said there wasn't enough points to classify that as a person. So that's a problem. And it's not a problem that's going to go away. Now, on Tuesday, the student ran in, hey, I got a new video. I've got that case solved. And I didn't bother to put it in the presentation because we'll have a new problem tomorrow anyway. So, but those are the kinds of things that cause, trouble to get out of there. So I'm going to go to issues. A lot of you say it has to work 100% of the time. Nothing works 100% of the time, but that's not the real issue. Oh, boy, I got 40 seconds. When the system realizes that it's having trouble, it has to be able to turn over to the human, in enough time, things like that. So the whole system has to work 100% of the time, let me put it that way. I worry about, maybe this is what I should have said, the stuff I worry about: sensor performance, poor environmental conditions, false positive negatives. This is one I think Dr. Clausen's going to talk about, is things like this. Is if I'm in the vehicle, do I want the vehicle to explain to me what it's doing? I feel better if I see this map and I see little boxes around the other vehicles, that it's identified them, and I'll feel better. I'm not grabbing the wheel, though. And then the communication issue, I think that's going to be a really big plus, vehicle to vehicle, legal, ethical issues. And so what I'm going to end on is I got two videos, and I think this is from Vietnam. So I call it the intersection of the present. And some of this guy here. So, but nobody is, maybe it's efficient. They're all moving. Nobody is stuck. So we go from that. And I found this, it's at low resolution, and it was the reference, it was from France. But here we go. They put a lot of time into this, I believe. So. And it goes on for a little bit longer. So, that's definitely not what Gainesville looks like today. So thank you for your patience. Again, try to give a sort of a quick shotgun overview of the technologies that are out there. And we're going to turn over to Dr. Clausen now for the next.
So, after all of that, I feel very compelled to represent and to present the human perspective, to be able to see how folks are experiencing all of these exciting but also challenging times as we are really standing in the transportation revolution. I'm an occupational therapist, so what OTs are doing is we are interested in the person, the vehicle, and the occupation, or those meaningful tasks that each one of us have to do to be able to survive, to strive, to thrive, to live meaningful lives, and of course to drive. So from that perspective, I'm going to talk about a study that we've conducted at the University of Florida to look at older adults' perceptions of autonomous vehicles. So I'm going to use the scientific outline to be able to frame my presentation. So it's going to be a true scientific presentation. And a little bit of background in terms of older drivers or older adults. So we know that the demographic shift in America is happening, and about 20% of the US population is over the age of 65, and that is to increase in the next 10 years so that we will have 1 out of 4 drivers will be over the age of 65. Despite the fact that older drivers have issues with medical issues, declines as a result of the normal aging process in their cognitive, their visual, their motor, and their sensory functions, as well as being on complex medication regimes, they are, and that causes that they are at a higher risk for crash-related injuries and fatalities. Despite that, driving is still the preferred mode of transportation among this population. So autonomous vehicles may hold excellent opportunities for these drivers to offset some of the health as well as the safety issues. Recent perceptions were measured by survey only. When older adults were asked about autonomous vehicles, survey only. So we thought, well, if we can use the surveys, but if we can also expose older adults to some of these autonomous vehicle technologies, what will we see? And the expectation that we had going into this study was that their attitudes, their perceptions, their values, and even maybe their early adoption thoughts may improve as a result of exposing them to some of these technologies. So what we did is we exposed them to a driving simulator that was programmed at the SAE level 4, and we also exposed them to the autonomous shuttle, the one that Dr. Lilly showed in the previous presentation. So obviously, because we are working with human subjects, we had to go through ethics approval and received a full IRB approval. That's the Institutional Review Board approval from the University of Florida. And we developed a repeated measures crossover design, and I'll say a little bit more about that in a second. We recruited the participants from the North Central Florida area, but with a concentration in Gainesville. And we included folks if they were at or older than 65 years of age, and if they had valid driver's licenses. And the exclusion criteria pertain to their performance on the Montreal assessment, cognitive assessment, and using the indicators of that particular assessment to understand cognition and cognitive declines. We had a variety of measures that we used, and I'm not going to go over all of them, but on the left-hand side you can see some of them pertain to clinical tests looking at set shifting as well as user perception surveys. And then also the driving habits questionnaire, which basically calculates or describes older drivers' habits, and the life space questionnaire that help us to understand how older people are moving in their home, outside of their home, in their neighborhoods, or do they even cross state lines as well. So, let me just go back to this one. On the right-hand side, you see the RTI, High Fidelity Driving Simulator. So in this simulator, it's got a full car cab, and the older driver would sit behind the wheel with a research assistant in the passenger seat. There's life-size images that's been projected on the actual screen. And folks, all the experiences are a very immersive experience with very high, what we call physical and emotional fidelity, meaning that the believability of this situation is really high. On the bottom is the TransDev Easy Mile Easy 10 autonomous shuttle that's also been programmed at the level 4 of the SAE standards, and that's the shuttle that we've used. In this particular shuttle, we had 6 older adults at a time in the shuttle, and we had a research assistant as well as the safety operator accompanying the older drivers. And because of the not having the actual NHTSA waiver to run the shuttle on the public roads, we conducted this study in a bus depot in Gainesville. So after folks enrolled in the study, they completed all of the baseline measurements that I've mentioned in the previous slide in Visit 1. And then they were randomly allocated to Group 1 and Group 2 because of the crossover design. So for folks in Group 1, they were first exposed to the simulator, and then they were exposed to the shuttle. And after each one of these exposures, we actually used the AV user perception survey to look at their perceptions prior to exposure, exposure after the simulator, and exposure after the shuttle to see if there's any changes. And then Group 2, we flipped the order of the exposure, and they were exposed to the shuttle first and then the driving simulator. So we collected the data by trained research assistants, and we entered that in a REDCap system that adheres to all of the privacy and the confidentiality policies at the University of Florida. And our analysis was conducted with statistical software, SPSS version 25. And today I'm going to give you a preliminary look into the data that we found. We haven't completed the study yet. We are enrolling 105 older adults, and this is 69 older adults that's completed the study. So please see this as preliminary data, and of course we cannot make any causal conclusions as a result of that. I just want to say something about the user perception survey. when we started the study, there were no user perception surveys that actually asked the questions that we wanted folks to answer. So we had to design our own user perception survey. So this is still undergoing psychometric testing, and so it's in development as well. But some of the things that I would like to highlight is that we basically have 28 questions on the table over here. Oops, the pointer is not working, but you can see that there's a total of 32 questions. 28 of them are all questions pertaining to perceptions, values, beliefs, and experiences with autonomous vehicle technology. And then we ask 4 open-ended questions, so such as the disadvantages or the advantages of autonomous vehicles. So all of these items derive from basically the dimensions, which is in the top left-hand corner. So we look at questions pertaining to trust, safety, control, experience, etc. And all of those dimensions are basically conceptually embedded in some of the existing models. That's at the bottom. There are 7 existing models. So as I say, psychometric testing is continuing with this particular survey, but this is the survey that we use for this study. So if we are looking at the results, so this is some of the demographics of our participants. So for shuttle first exposure, we had 20 women and 18 men, and the women were a little bit younger than the men in comparison. So 73 was the mean age, 77 the mean age of the men, and that pattern pretty much held for folks who were exposed to the simulator first as well. If we look at the gender distribution, we had so far 29 men, that's 42% of the sample, and 58% female, and that's a pretty good representation of the current demographics for gender according to the Florida census statistics. In Florida, it's 45% male and 55% female. If we look at racial distribution, so we had 87% of the folks that self-classified as Caucasian or white, 9% classified as black, and 4% classified as other. This is an interesting slide in terms of the actual education. So Gainesville being a college town, and much of our recruitment occurred amongst the older adults in Gainesville, you can see that 73% of our participants had either bachelor's degrees, master's degrees, or doctorate degrees. So that is totally, of course, skewed in terms of the general population. We also had 23% of our participants having a technical school, some college, or an associate degree, and 4% of our participants had a high school diploma or a GED. So a little bit skewed in terms of education, so we worked with a very highly educated group in the study so far. Right, so I'm going to show you the results of the entire group before the actual exposure to any of the technology and then exposure to the shuttle and the simulator. So a brief orientation here is that on the y-axis you will see the user perceptions, and we measured that with what we call a visual analog scale. And so that's a scale that is numbered from 1 to 10. It's exactly 100 millimeters, and we use that as numeric data to be able to measure the perceptions of older adults. And on the x-axis, we have the baseline condition, the shuttle condition, as well as the simulator condition. Thanks, Lily. So the variables on the right-hand side pertains to the social influence, the intention to use, and the cost. And all of these, if the graph is going up, it shows that older adults are more favorable to each one of those conditions. So you can see that was the case for being exposed in the shuttle as well as in the simulator, although there was a dip when folks were exposed to the simulator. The outlier here is the intention to use, where the older adults were really more positive after they've been exposed to the simulator, and the intention is, of course, to use autonomous vehicle technology. For the actual next 3 variables, this is pertaining to how media influence people, as well as their trust of autonomous vehicle technology, and the controls. Do they want to take control over of the vehicle, or would they rely on autonomous vehicle technology? You can see that the graphs are pretty much telling us the same picture. At baseline, they are lower. Once they get exposed to the autonomous shuttle, sharp increases, and then to the simulator, we see that the graph is decreasing again. And then our last 4 variables pertains to authority, that's pertaining to trusting the National Highway Traffic Safety Administration's safety measures, perceived usefulness, perceived ease of use, as well as safety. And in each one of those cases, again, you can see that folks felt much more positive to these 4 variables after they've been exposed to the shuttle versus being exposed to the simulator, but still the simulator had an effect. So if we then looked at what happened in the groups, so if we look at group 1, you will see that they were first exposed to the simulator and then to the shuttle. Now, I don't want to be saying that we can make causal inferences, but we did look at statistical significance, and that's outlined in the red font over there. And we also looked at effect sizes to tell us how big the effect is. And what we learned from this first table on the left-hand side is that the older adults' trust increased quite a bit after they've been exposed to the shuttle last, as well as their perceptions of safety after they've been exposed to the shuttle last. And then for group 2, where they've been exposed to the shuttle first and then the simulator, we see that the intention to use increased. So we think it's because in the simulator they were sitting behind the steering wheel. It felt like they were an operator of the simulator, whereas in the shuttle they were more passive as a passenger. Okay, so my take-home messages, overall analysis, exposure to AV technology positively affects older adults' perceptions to this emerging technology. Perceived safety shows the highest percentage points of increase after being exposed to the autonomous shuttle, and then intention to use shows the highest increases after being exposed to the autonomous shuttle. To the simulator. The within group analysis showed us that trust and safety significantly increased if they were exposed to the autonomous shuttle last, and intention to use significantly increased after being exposed to the simulator. So our next steps is then to do, of course, to complete the study and to look at gender and age and time effects as folks are being exposed to this technology. This is also laying the foundation for us to further look at folks who are disabled, those with dementia, the disadvantaged, the de-skilled, as well as those with degenerative diseases such as the degenerative neurological disease. Because we do believe that transportation, like Mr. Leonard had said, do not just need to be affordable, effective, integrated, and ubiquitous, but for these special populations, it also needs to be accessible, acceptable, adaptable, and available. And so, we hope to further the work in that area. So I want to acknowledge our funders as well as our stakeholders, and then each one of the project team members, specifically Justin Mason, our postdoc, Dr. James Versell, who did much of the data collection, Virginia CCO Pico, one of our collaborators, Jason Rogers, and our research assistants, Melissa Varera and Casey Clark. So thank you so much for your attention.
So I think we are slightly ahead of schedule, right? So maybe I can take a few more minutes. All right. Let's just make sure. All right. Good morning. I'm Sanjay Ranka. I'm a professor in computer science. I do mostly artificial intelligence for transportation and healthcare. So what I'm going to talk about today is the world is changing, where in the past, most of the data in transportation was collected by the government or third parties like Google. But now with autonomous cars, all the car companies are going to also be having data, and that's a new player in the market. And the key goal is to be able to create a symbiotic relationship. And in my mind, the way to do that is make things more real time, because at some juncture, all the cars which are driving around, they have to interact with pedestrians and other vehicles. And the more real time information which you can provide to them, the more amenable they are going to be able to use it. And obviously, that's going to improve both safety and operations. What we are trying to do is we're trying to build a data store, again, try to be able to access that in real time, to be able to achieve a variety of applications, both from monitoring, from evaluation and analysis, be able to do predictive modeling, be able to do optimization of a variety of issues in signal and corridors, and also support planning and investments. Again, the key goal obviously is to both manage traffic congestion and improve safety, but make everything data driven. And also be able to support efficient movement of goods, services, and people. With that challenge, I'm going to talk about some of the projects which we are working on trying to make the infrastructure smarter and more real time. The goal is at a very high level to be able to compute everything on the edge, as they call it, right near the signal, as close to the signal as possible, because you want to make it real time, and then be able to assimilate key findings and push that to a centralized environment like a cloud so that you can do more longer term analysis there. Clearly, the important part here is to be able to be resource efficient and be able to use a variety of sensors which are available to you today and which will be available to you in the future, and that's what we are working towards. So one of the projects which we are working on is what I call smart intersections. So the idea basically is that you have an intersection, typical intersection in any city, which has loop controller data today. There are loop controllers under the roads, which give you data about every vehicle arrival. We want to be able to use other cameras, like video cameras, which are called fisheye cameras, sitting on top of the intersection, and in the long term, be able to use LiDARs and other sensors to be able to collect information in real time about all that's happening on the intersection, store it in a sensible form, keeping track, making sure that we obviously worry about privacy issues, and then be able to understand what's going on at the intersection in terms of anomalous behavior or in terms of near misses, to be able to provide feedback to planners as well as architects of intersections on what designs actually are more effective and what signal timing plans actually are more effective to improve both operations and safety. So what we're trying to do is we're trying to develop these real-time scalable systems which can actually collect data from loop controllers as well as from video. First, I'll talk a little bit about the loop controller part of it, and then I'll talk about the video analysis. To be able to collect the data in real time, to be able to run all these algorithms for detection and everything else in real time, and be able to then push that information back to the autonomous vehicles in real time for this to be effective. So we are developing the system for understanding what's happening at the intersection, both at an intersection level and as well as at a city level. We work both with City of Orlando and City of Gainesville, collect information from all the signals which they have data for to be able to analyze it. And I'll show you some of the results from a broader perspective and then go back to the intersection level. So for example, in this particular case, we can actually process 1 week of data in less than an hour. And that's our goal. Our goal is to make everything as real time as possible so that the information which is gathered is captured and processed and analyzed and sent back to the vehicles and the pedestrians. We can actually take all the data in a given city, rank all the intersections in terms of their performance so that traffic engineers can understand what's going on at every intersection and get a broader picture of. I'll give you an example of this, where essentially what it will do is it'll rate, if you look at one, it shows the different categories of intersections, whether detectors are not working properly, or they have capacity issues, or there are timing issues. Again, the intent basically is to provide a traffic engineer with a good perspective of what's going on in the entire city so that they can make changes in real time in some cases, or at least at a daily basis. So they can select all the information about what's going on in the city for any given day, be able to figure out the weekday versus weekend behavior, to say, hey, this is where my problems are during the weekdays and the weekends, understand what's happening in the morning, what's happening in the evening, so they can plan the traffic signal timings better. Again, the goal is to make the infrastructure smarter so that they can interact better with the traditional and autonomous vehicles. So this one kind of shows you that the behavior changes by the hour and how do you plan for that. Also, be able to do a change detection automatically to say where the change is happening so you can focus on those changes. This kind of gives you an idea in terms of a broader infrastructure. What I'm going to now talk a little bit about is how do we do real-time video analysis to be able to understand what's happening at an intersection and again be able to generate messages on the fly and be able to support in a few years information to the autonomous vehicles about what information is useful for them, what's happening in the city, if there's for whatever reason there's an incident, and at another intersection, can they change their route dynamically? So this one kind of shows you, again, real-time processing of an intersection in Gainesville, where traffic is coming. We're tracking different kinds of objects. In this particular case, I'm showing you in real time all the cars. The greens are a bike or a motorbike, and the yellow is pedestrian. So all this tracking is happening in real time. Also, this kind of gives us a good synopsis of what's happening at the intersection. We collect this data in real time and then process it to understand behavior. You see this video is playing again and again. What this does is it gives us information about all the vehicle trajectories on that particular intersection. So these are color-coded for different directions. All the trajectories are marked so that the light ones where they start and the dark ones where they end. And this shows you the behavior at that particular intersection. Again, the goal is to be able to analyze this and be able to rate all the intersections in terms of their safety and operational quality. This shows you the behavior on the right-hand side based on different phases. Generally, every signal has 6 to 8 phases, and each phase has different traffic behavior. In some cases, people are going east-west. Some cases, people are going north-south. And then be able to also understand what's happening on a given phase, because traffic sometimes moves in a fashion that two directions can interact with each other. So we can actually show that. We actually then are able to analyze also all the pedestrian trajectories on the intersection. So see how many people are actually jaywalking on the intersection, how many people are not following the paths. And again, we can do this for morning times, evening times. The other interesting part which we do is we look at anomalous behaviors, right? So for example, these are all the trajectories here which show you the vehicles which are crossing on the red light in a given hour. The key goal of all this is that once I can analyze this data, we are able to then predict behavior and then be able to use that for better intersection design. And in some cases, then the end goal is to, if you look at the left, there's a pedestrian crossing the traffic and goes back, right? So we want to be able to capture that kind of behavior and be able to warn all the traffic on that intersection to say, hey, there's a pedestrian crossing where they should not be crossing, be aware of it. So these kind of real-time messaging and real-time processing is very important to improve the safety in the long term. And the goal is that any object which can actually communicate at the intersection should be able to get that piece of information. Here's another example. If you look at the behavior of this particular pedestrian, they come there, there's a red light, doesn't want to wait, comes back and J crosses. So we want to be able to track all this behavior in real time and be able to send this information to all the vehicles on the intersection. We also want to be able to detect near misses. So if two vehicles are coming very close to each other, we want to be able to say, hey, there's a potential problem there. And the key challenge, of course, there is that we're dealing with spherical cameras, which have distortion of all kinds. They see better near, and they don't see very well far away. We have to be able to take care of that. And then, again, be able to find out. So here's an example. On the top, if you see there, that vehicle suddenly stopped in the front. So the vehicle behind braked. And if it didn't brake, there would probably be a crash. And the vehicle possibly braked in this particular case because there was actually a fire truck behind, which was beeping. So the vehicle in the front stopped in the middle of the intersection, and the one behind went further. Another example of that if you look at these two vehicles, they come very close to each other, but that's normal behavior because they're just passing each other in different directions. They came very close to each other, but they're in different directions, and that's not really a near miss. So we have to be able to detect both things which are real misses versus quote unquote the false misses, if you may. So we do this analysis by collecting the data in real time, and then part of our project, Lily mentioned this, to be able to do this in the trapezium project, where we will have all these video cameras at 10 out of these 23 intersections. We'll collect the data and be able to essentially share the data with the smart and connected vehicles in real time about what's going on in the entire network. Be able to analyze the network itself, detect all the incidents which are happening on different parts of the network, and relay that back to autonomous vehicles, and be able to optimize at the network level. We also do other work on the infrastructure side, where we understand by looking at vehicles which are passing on highways to be able to say what commodity are they carrying. One of the interesting parts of understanding behavior on highways is to understand how commodities are getting transferred in the state of Florida, and obviously this can be extended to the entire nation by essentially looking at the type of object and logo detection of what company it is. So if it's Walmart, we know what kind of goods they are carrying. If it's FedEx, we know what kind of goods they are carrying. So we can understand in real time how goods and services move around in terms of freight planning and everything else. The other thing which we do is we look at highway videos to understand how vehicles enter and exit ramps. How does that impact speed of the different vehicles which are coming in? To be able to then understand what kind of ramp changes need to be made, or what kind of designs are better than other ones to be able to be effective. This is my team. There are 4 faculty involved in this project, and 8 or 9 PhD students. We effectively develop a variety of these techniques. I'll leave it, our work is supported by NSF Smart Cities Project and FDOT. I'd like to acknowledge them. Also, this is a McKinsey study which showed the importance of different levers in terms of improving transportation. It just came out 6 months ago. And UFTI as a whole is focusing on the top 5 there, which can actually have a real impact in terms of improving traffic performance. Thank you.
Thank you. Do we have a few minutes for questions, I believe? Oops. Yes, please.
Thank you for visiting us. We're an academic institution, so we'll give academic reactions to what you've said. I'll give you 4 quick ones. For your presentation, what you've discussed about improvements in autonomous vehicles at intersections could be done now. Nothing preventing that from happening now. So it would be useful to think a little bit about the political economy of why is it we aren't doing these things now, and we're going to need autonomous vehicles to get them done. I'm not saying you answer it, but it might help to sort of motivate what's going on. I'll go quickly through the 3 other ones, and these are largely for motivation. On your presentation, you show the sort of stylized facts about the declines in fatalities per VMT. True, nothing obviously to dispute about that. The issue is why. We're really not so sure about that. I mean, one can speculate about improvements in vehicles, but it's very hard to show that kind of thing. I would suggest that an equally compelling explanation is the increase in congestion that's occurred at the same time because people are going slower, it's simple physics. Point being, that's a benevolent way to reduce traffic fatalities, is congestion. And the point that I would make is that we're sort of running out of good ways to save lives. And that's where autonomous vehicles comes in, because that's going to be able to accelerate the decline, and that's a good thing that's going to happen. On yours, you didn't have time probably to go into detail, but it'll help to know more about the people in your sample. In other words, what was their accident experience? Have any of these people been in accidents? Do they know people who've been in accidents? How much VMT they drive every year? They care about safety in the vehicles they buy. You know, going into this, this would be an interesting comparison. Are there groups of people who we think, because of their own experience, vehicles, and so on and so forth, are going to be open to the benefits of autonomous vehicles and safety as compared with others who aren't at all similar to those experiences, will obviously be very, hesitant to believe that for a variety of reasons. It might be interesting to sort of point all that out.
I'll comment on that by just saying that we do have that data, and so that will be analyzed as we are done with the entire year.
Yeah, that'll be important, I think, in terms of the people who resisted. And on yours, I think the thing I'm thinking is long run. Is the road network going to change because of autonomous vehicles? Remember, we have built this network based on non-autonomous vehicles. And I'm seeing all these intersections, and I'm thinking, yeah, well, we had that because people couldn't get close to their destination, and they got to walk across city streets. So maybe traffic patterns will change. Maybe we'll realize, these kinds of intersections are bad, roundabouts are better, or for that matter, we don't even want these kinds of things. It doesn't hurt to start treating now the changes in the network that will come about because of autonomous vehicles and start speculating. Obviously, you can't do any of this now, but I think that we're going to learn a lot as we go into this, and we're going to see both pedestrians and the network changing. So those are suggestions to help you.
Okay, thank you. Yeah, with respect to your question, if I got it right, yes, we can start doing this now. One of the issues is the chicken and the egg. The vehicles need to be instrumented. The infrastructure needs to be instrumented in order to communicate. I think that's what is unique with what's happening in Florida is that both are happening at the same time, and that allows us to start getting those benefits. Carl?
Just going to say about the, I have to hit a button, about the congestion. That's a very good point.
Oh.
Push and hold, or
There we go. That's good.
how about now? Anything?
Yes.
Okay.
Yes.
All I want to say about the congestion was that's a very good point that I hadn't thought of, but it's definitely not what I want to see happen. But that's an excellent
Yeah.
point. Yeah.
Quick comment. The infrastructure unfortunately doesn't change overnight, right? So all these highways and road networks are built over decades. So I know that these things are going to stay for a long time. We have to work with whatever we got right now. And of course, as we learn more, as you're pointing out, they will evolve, but probably take several decades before that happens.
Any more questions? Yes. Mike's coming. Yes.
Okay, urban planner, it strikes me this is fascinating, and the big data revolution is giving us tremendous resources, but where do we draw the line between rational human behavior and irrational human behavior? Because theoretically and totally unacceptably, you can have, collect the entire, data on the entire history of one pedestrian who is apparently trying to cross the road. The mental history, is he out of an institution? Might he have a relapse? Does he have something in the family recently? Yeah, we have the data about that. Yeah, his wife is behaving. Where do we draw the data? Where is the human responsibility in that? And not ours and yours as scientists, but ours as individuals. Thank you.
I think one of the points Sanjay was making was the real-time information and warning, and so being able to recognize or predict intent that's I think where that technology can be very useful. Okay, more questions?
But you know, just to add to what Lily just said, the doctor can only tell you what you need is good for your health. If you still want to do stuff which is bad for you, at some juncture, we can only prevent other people from not getting impacted.
Yeah. There's over there.
Thank you. I just saw an article online where the Attorney General is ordering that software always be created with a back door so that government can access it. Of course, wherever there's a back door in technology, hackers can misuse it. What are the provisions for encryption security in autonomous vehicles? Will they have no back doors so that no hackers can intrude? And to follow up on the previous gentleman's point, we probably all remember the Geico commercial where the squirrels are like high-fiving each other for tricking a car and running off the road. What happens when 15-year-old kids see autonomous vehicles coming along, decide to kick a soccer ball across the street and watch what happens?
Yeah, on the second part, I think that's already happening, and these are just anecdotal stories that I've read online, but people challenge the autonomous vehicle. You know, they'll drive right in front of it because they want to see what it does. And that's a problem. The encryption part, I'm probably gonna have to pass to Sanjay myself because the level that I've been at is just got to get it to work, and that's becomes kind of my secondary concern. But boy, if it is hacked into, it could just be chaos. I don't know. Do you have any comments to add?
Yeah, I don't really know much about the security of autonomous cars themselves, but on the infrastructure side, we are making sure that whatever we actually collect, we throw away as soon as possible. So we don't, like for example, the video part which I talked about, we just need it for 5 seconds, and after that we process it, and at that juncture, the video is useless for us. We just want to get the meta information about what's going on. We obviously are very careful about privacy issues, and we encrypt all the information which we keep. We anonymize it, that even if you were able to get to it, it's useless for you. Because our goal is not to track people, our goal is to understand behavior.
Yes, there was over there.
Thank you. My question is about the connected infrastructure and the infrastructure pieces. Because I know in the autonomous vehicle community, there's an actual competing theory, including one that's being tested right now in Florida at the villages, where they want to be completely independent. They don't want this connection. They don't want to have to depend on the infrastructure being there, doing what it's supposed to. They want the vehicle to be smart enough and the mapping to be good enough. So I want to sort of talk to you about, get your take on what this debate is about connection versus true autonomy.
Yeah, this is a very interesting, I guess, competing approaches. And in my view, you need to have both to maximize safety and to avoid making congestion worse. I don't think it can be done without the connectivity, just purely with autonomy. The information that you can get with connectivity supplements very nicely what autonomy is able to do. So in my view, the two have to work together.
Yeah, I was gonna say when it all started, like 2007 was the urban challenge, and you didn't want to rely on anybody. It had to just be you. And part of that, though, is look at the impact cost of the infrastructure. So we had no impact on the infrastructure, and yet you could get it to go. But the benefits are, if there's other vehicles, especially pedestrians, this is one of the projects we're doing now, is that if I can be told that from sensors at the intersection or from other vehicles or whatever, that information is just really going to help me. So again, when we started, well, there is nothing, so we're just going with the current infrastructure. But I think anything that's added is just really going to be a benefit. So.
Yeah. Okay. Yes.
So a good segue for my question is, so if these autonomous vehicles are relying on the connected infrastructure, and as we all know that things break at one point in time, where is the line that you will draw in terms of how autonomous systems are supposed to be just self-sufficient, right? Because otherwise, people will start taking shortcuts and build systems relying on the infrastructure that may fail and may create some potential hazard.
I was just going to offer my opinion is I think it ought to be self-sufficient, and anything I get in from any other source is a bonus for me. It's going to make me better. But I think it's going to have to be. And as it all develops, too, I mean, we're in north central Florida, and you don't have to go very far to be out to not much infrastructure. Well, I don't want to take that back. To, minimal things. And I think the self-sufficiency is going to have to be with us for a while.
So by definition, most autonomous systems are fail-safe. That means they will work independently, maybe at a lower quality than expected if the information is not there. And the goal is that they become more efficient as more information is available. But the intent always is that things should work even if everything else fails.
Yeah, I think there has to be redundancy. I also think that deployment will be facilitated if both work together to supplement the information that the autonomous vehicle has right now. For the examples that I showed, for example, where you don't have line of sight to obstacles, but having information from the infrastructure allows you to get that. Okay, over there.
Yeah, I'm sorry I was late. Maybe you covered this. Thank you. But I was wondering about a time frame. A lot of people say this is going to happen much later than what we think. And maybe this is another group, but supposedly the 5G network is very important, and China's way ahead of us, and we're arguing with Huawei, and are we going to use them or not use them? Supposedly it'll be a security risk. And so I was and also trucks. Now those are high-paying jobs, truck drivers. Are you just doing vehicles now, or will they be doing trucks later? Is one I've heard that there'll be one lead-in truck with one person and then autonomous behind it. And I'm wondering if a young person, not I, but if young people want to get into this field, what's their best major in college, or what should they be studying?
Well, I just tell our students that the whole area is, and the last part is a mix of mechanical, electrical, computer science, and that you can major in any of those, but you're going to learn about all of those. Mm-hmm. So it's a blend. Maybe it needs to be a new major. I don't know, but
traditionally the transportation systems has been under civil engineering, but you see here the collaboration that happens at the research level. And we want to bring that also for the students. So we have transportation across different colleges, across different departments, and it becomes so much more important now with advanced technologies at the forefront.
It's funny, you go to different, electrical engineer is going to say it's all electrical. They're number one, and the computer person.
So I would say that the world is changing, where you could take one profession and work there for 35 years and you retire. I told my two daughters, just learn how to learn, and after that you'll be fine.
Yeah. All right, we are officially out of time. I put up takeaways from this session. From the different presentations, and we welcome more discussion. Thank you very much.
No, no. I was wondering if I could do it from there, but maybe it's better to come here. So I'll just do it.
I think it's better to come here so
Yeah.
you're not.
Yeah, yeah. Good morning. Howdy. My name is Swami Gopal Swami. I spent several years in the automotive industry, primarily in the areas of control design and development. And for the last few years, I've been with Texas A&M University working on connected and autonomous vehicles. So before I go on with what I'm going to talk about, let me introduce my colleagues and co-panelists. Dr. Darba is a professor in the Department of Mechanical Engineering, also at Texas A&M, with focus on control theory and applications, including, of course, autonomous vehicles. He has been working on vehicle platooning for over 3 decades and has developed some fundamental results that provide insights into platooning and connected vehicle operations. Dr. Ratnam is an associate professor in mechanical engineering also at Texas A&M University. His research interests include autonomous vehicles, ground and aerial, ground and underwater autonomous vehicles, vision and sensor fusion algorithms. Somebody asked in the last session what kind of education would make sense to be in this space. Just to give you an example of Dr. Ratnam, he has his bachelor's and master's in mechanical engineering, a master's in electrical and computer science, PhD in civil engineering, and his PhD thesis work was on aerospace. Okay, it's a great pleasure for me to be here to introduce the concept that we've been calling. Let me just see how I should. Okay, so the concept that we are calling as infrastructure-enabled autonomy, and the idea is how that leads to autonomy as a service and what the implications could be thereof. We believe it's a new paradigm for autonomous vehicles, and the primary goal would be to accelerate the deployment of autonomy, autonomous transportation. So let me start with this. Why are we working on autonomous vehicles? Many people have already addressed that before, and so I don't want to belabor that point. Yeah, there are tremendous benefits in terms of the potential for number of lives saved, number of crashes that can be reduced, the economic savings, the fuel savings, and so on and so forth. Obviously, great benefits. But we have to look at the fine print. The benefits accrue with a corresponding penetration of autonomous vehicles in the transportation. You need to have 90% penetration to kind of get the fabulous benefits that we see. Let me see if it doesn't work. Okay. The fabulous benefits that we are hoping to get. And remember, for example, in the US alone, we have about 250 million automobiles, both commercial and passenger cars and trucks, on the road today. And the question is, how do we hope to get the kind of penetration that we need to really get the benefit that we're all touting that we will get? And so that's really the thought process behind what I'm going to be talking about today. We talk about the penetration of autonomous vehicles, and let me kind of give a quick rundown of what people have been thinking. And I want to do this by using the famous Gartner hype cycle for emerging technologies to kind of quickly walk through what people have been thinking. In 2011, in the, I don't know if people are familiar with this hype cycle, but essentially it's just talks about the various emerging technologies that are there and the different phases of enchantment and hype about this technology before kind of you go into the trough of disillusionment and finally kind of get into the plateau of actual meaningful deployment. Okay, so the in 2011, autonomous vehicles did not have a space here. 2011, we suddenly started having autonomous vehicles, and as we walk through, you can see that there's a peak of its hype around 2015, and whoa, it started going down on the trough. And in fact, in 2018, I think I don't necessarily agree with that, but it's the autonomous stuff technology was split into two parts for different levels of automation, and one was continuing to be in the hype cycle, while the other one is going down in the trough of disillusionment. So the point is, as I said, we have 250 million vehicles on the road. How do we expect to accelerate the penetration of autonomous vehicles? Because that's the only way we can actually get the benefits that are being touted that we hope to get from autonomous vehicles. So I come from the automotive background, and so I have an acute sense of what it takes to, or I have an acute awareness of the realities of complex code. Because as you can see, mechatronic system, the modern automobile in general is a mechatronic system. The autonomous vehicle is much more of a mechatronic system, and the complexity is all baked into the software that goes into these vehicles. So we have, in a typical modern car, 100 million lines of code. The complexity is humongous. The number of subsystems, number of engineers working on it, number of suppliers involved, the distributed nature of the development. So the complexity is really enormous, and this is just for regular modern cars, not necessarily autonomous vehicles. And if you just look at some of the headlines, you just have to do a Google search, and this I did almost a couple of years back. There have been dramatic failures across the globe in terms of software-related failures. And when you have software failures in mechatronic systems, that is systems that work not only the software that works with mechanical systems and that which has interaction with the human beings, the costs and impact are humongous. So I'm not going to belabor the impact of the complexity, except to say that we need to really think about how soon do we really expect the people to be taking, for us to be seeing 90% penetration, even 10% penetration, 25 million vehicles on the road. I expect that we probably will have 20 to 30,000 vehicles in the next 10 years in a very limited kind of fashion. So here's my explanation. I want to say how to think about this. So if you look at the driving functions that we do today, you can look at the, let me see if I can get a pointer on this. Yeah. Okay, so the typical modern vehicle, you have a drive-by-wire system that is developed by the automotive OEMs. They help you, once you press the car, the gas pedal, it translates that into how much acceleration you need to get, how much braking you need to get, how much steering you need to provide. You have the decision making. Before that, we have the situational awareness. The driver, as you would see what's outside. You look at your dashboard, kind of make an assessment of the situation and do your decision making. And then you use, in order to drive, additional information that comes from outside. So the distribution of the responsibility amongst these functions, and the responsibility really translates to liability to a large extent, is as follows. The automotive OEM takes care of the green box. The human driver takes care of most of the decision making and situational awareness. And you have some excursions from the OEM onto the decision making by providing some supporting ADAS functions, advanced driver assistance systems, such as lane change, obstacle avoidance, and so on. The information comes from third-party players, such as GPS, cloud services, etc. And there are infrastructure providers, infrastructure primarily being information infrastructure providers who would facilitate the transfer of that information to the vehicle to do the driving. And this is a balance of a distribution of responsibility that's evolved over time, and we understand what it is, we are comfortable with it, and this is kind of where we are right now. If we want to move to a new paradigm of completely autonomous vehicles, what this changes to is the following. The automotive OEM really takes responsibility for the entire driving. And this is where I believe there's going to be a big pause in the introduction of autonomous vehicles in a big way. Yeah. We've already seen many accidents, accidents of that nature. If it were to happen for a large company with selling millions of vehicles, it's going to be a big liability for them. So I feel that this will provide a lot of big pause, and so at best we will have 20 to 30,000 vehicles, maybe on a leased basis, they're owned by the OEM and provided on a very limited circumstances. And that does not bode well for our goal of 90% penetration. So what is our proposal? Our proposal is to separate this intelligence that's going to be in the needed for autonomy, for autonomous driving, from being only in the vehicle to being separated between the vehicle and the infrastructure. Take advantage of the infrastructure in a very fundamental way, and that would reduce or at least distribute the liability, and that is kind of what we want to propose as a concept, as an additional in parallel development along with the existing approaches for autonomous vehicles. So the idea is that we have the traditional driving that's taken care of by the automotive OEMs that will continue to remain there, but the situational awareness will come from the infrastructure. I say from the infrastructure, I mean primarily from the infrastructure, and the decision making will be done by third-party units that reside between the drive-by-wire system of the vehicle and the situational awareness on the infrastructure to help make the autonomous driving decisions. So the core concept is what I consider as the separation of issues and expertise. The automakers will focus on the drive-by-wire capabilities and make it even more perfect. They can, of course, bring in more advanced driver assistance systems. But then the infrastructure will become smart and start enabling awareness. And when I say smart infrastructure, what we mean by that is that the perception and the contextual awareness will be synthesized using off-board sensing. So you will have roadside units that will have sensors that will generate, that will be looking at, so you essentially have eyes on the road, but placed on the infrastructure. They will be looking at the road from above, generating the situational awareness information, sending that wirelessly to the vehicle. And in order to do that, we leverage connectivity. That's there was another question sometime back, which one should we use? Should it be connectivity or should it be autonomous driving? We believe it has to be a combination of both. There has been significant improvements both in connectivity as well as autonomous capabilities in the recent past, and we need to really bring them together. And what this allows us to do, very interestingly, is this allows us to do on-demand automation, and I'll talk about that later on, because that actually suddenly opens up a possibility for funding this infrastructure investment required that would not be otherwise possible. Here is a cartoon that kind of describes our concept vision. So you have the specialized corridors that we will call as the infrastructure-enabled autonomy corridor, IEA corridor. These will have roadside units. They may look like street lights, but in reality, they are multi-sensor smart packs, multiple sensors that can essentially look at your road and generate situational awareness information. And of course, you don't want to collect all the information and send it blindly to the vehicles, but you have edge computing right there on the edge to abstract that information to the minimally required amount of information that can be sent optimally to the vehicle in a wireless fashion. Then that information then comes into the vehicles which have the drive-by-wire capability, the smart connect device inside, which can talk on the one hand to the infrastructure, on the other hand to the vehicle's driver-by-wire system, and use the information to generate autonomous driving capabilities. Once you have that information, it does not have to be used only for autonomous driving. You could imagine a plethora of uses for such information. It could be sent to a bicyclist or a pedestrian on their smartphones or a smartwatch to give them warning signals of what's happening on the roads. You can send it to manually driven vehicles just as diagnostics and information so that they can drive better as humans. So this is the fundamental concept that we have been trying to promote as infrastructure-enabled autonomy. And let me first walk through a few slides that explain how we have been taking this concept at Texas A&M University. So we started by actually having a clarification on the concept by doing a theoretical exploration of the risks using a probabilistic characterizations of the faults and risks associated with distributing the intelligence. So we demonstrate that the risks gets distributed according to the based on the proposed redistribution of intelligence, where we assume that there's a clear partitioning of the functional physical interfaces. Dr. Ratnam and I actually co-authored a paper on this, and it's the paper's reference is right here. So that's kind of laying the theoretical underpinning for why we would want to work on this concept. The next one was our iteration 0 work. This is where we said, okay, let's now do a virtual simulation of this concept to see if we can demonstrate that things could work. So we have simulation of autonomous vehicle with three, some of the students who worked on this are right here actually in this room. We actually have 3 cameras that, 3 roadside units that are simulated, and the vehicle goes through each of these cameras, and the vehicle is able to detect the, a camera system is able to detect these vehicles, localize that, send it wirelessly, and for wireless communication, we use DSRC units. And the reason we use DSRC unit is not because we have a preference for the DSRC over 5G. We are actually communication agnostic, but we were donated 30 DSRC units for free by Denso Corporation. And that's the reason we use that. But the idea was that the fact that we could use the DSRC implies that's actually one of the lower bandwidth communication capabilities, and we have been able to successfully use that to demonstrate our system, and the implication being that if 5G were to come on board and if you adopt 5G, it's just going to be that much more easier to do it. So that's the iteration 0. The iteration 1 was development of a prototype at our Release campus. Is this the same presentation that I sent you? Sorry. Okay, this is, what's the title? Sorry, can I just ask the title of the presentation? I don't see it anywhere here. The title of it? Yeah. It's titled Your Name. Okay, all right, that's right, okay. Okay, so this is our first iteration. And essentially what we have is we have a Release campus. This is old military Air Force base that we are using. It's got 7+ miles of concrete runways that we use as innovation proving grounds at Texas A&M. It's called the Release campus. And that's where we did our initial prototyping experiments. You can see that this is a mobile trailer that has a pole sticking on top of it. We have a camera mounted on top of it. We have wires coming down. We have a laptop serving as the edge computer. And this is the autonomous vehicle that we use to evaluate this capability. So that was the first iteration 0. Then the iteration 2. Before that, I want to show a couple of more videos because let me. Yeah, so this is how it looks like. For example, this is the trailer. The camera is somewhere here. There is an edge computer here that communicates to the vehicle wirelessly through DSRC. And you can see from the camera, we can actually track the vehicle and localize the car in terms of the runway and send it to this vehicle. Yeah, this is what I want to show. This is Texan research, so we have to have the hat. But so this is our very first experiment where we were just doing simple lane changes and so on. This is the Relish campus that I just mentioned. It's a 2,000-acre sorry, not old, 2,000-acre military air base repurposed for advanced technology research. We have 7+ miles of connected concrete pavement. We have traffic intersections, specialized roadside units, and 5G connectivity is in the plan. And this essentially becomes our smart city environment that we want to work with. So if we look at the IEA development, how it has moved up to now, on the iteration 2, we have built a 450-meter course with 4 roadside units. These are essentially luminaires, street lights, on which we have mounted the cameras. And let me see if I can, yeah. And this is connected through a wire to the edge computer at the bottom. We are still using the laptops for now because we are still in the development phase. But the idea is this can be now made to switch between DSRC or 5G or any other communication method. And we have used this for a variety of testing. And that's kind of some of the testing is what you will be seeing later in the presentations also. And so we have 4 of these light units, about 50 meters between each of them. And these are not powered, so we had to actually have generators for each of those when we are doing our experiments. But this kind of is the beautiful landscape that we get to work with. So some recent tests. So this is multiple views. You can see the first camera tracking the vehicle, and then there's a handoff that happens at some point when the vehicle comes into the view of the next camera, and then there's an overlap period. And after the overlap period is over, the second roadside unit takes over, and they are constantly processing the information, localizing the vehicle, sending that information back to the autonomous vehicle. The autonomous vehicle has a multiple set of sensors because it's being used for a variety of research purposes. But for this particular project, they didn't use any of the onboard sensors. So they relied exclusively on the information coming from the infrastructure, because that's kind of what we wanted to demonstrate. So what I want to say is this is a concept, obviously, in its really early stages, but we have already been able to show enough progress that we feel compelled that it's now really time to take it to the next stage. So the technical value proposition is that the multiple sensor smart pack, you can get much higher, reliable, and precise information because you know the ground truth on these roadside units. Yeah, so you know the ground truth. You can have markers on your road. You can have reconciliation between the different roadside units. Within a roadside unit, you can have multiple sensors that are fused with each other. And not only that, you can also have the ability to avoid occlusions. So if you're driving today, if your view is blocked by a vehicle, a truck or whatever other vehicle that might be in front of you, you really cannot do much. And the same thing applies to sensors that you mount on the vehicles. You can only do so much with the sensors that you mount on the vehicles. And this is exactly where sensors with a different vantage point dramatically changes the clarity of your situational awareness. And then the fact that you have increased computational time, you can do much more in terms of understanding what is happening to your traffic. You can spot potholes. You can identify traffic jams. And most importantly, every vehicle will have the same sort of belief states, shared belief state that is common between all the vehicles, so they know how to try to respond to each other. And mind you, I'm talking about a scenario where it is a mixture of manually driven vehicles and the IEA-driven vehicles. Now, this is the interesting part. What this whole concept allows is provides a new paradigm for doing autonomy. Yeah? The deployment model, how exactly are we going to do autonomous vehicles? So my expectation is the following. I would be driving a vehicle that looks like a normal vehicle. I would be driving it in general as I usually do, except when I go to these congested areas that have an IEA corridor. My commute time, for example, that I spend 1 hour every day, that's when I say, no, I will actually want to go to these IEA corridors. The corridor will interrogate me as soon as I enter there. Say, do you want to be driven autonomously? Of course, there has to be a registration process prior to that. Let's assume that's done. So it interrogates, say, hey, do you want to be driven autonomously today? And if I feel like it, I say, yes, I want to go here, and it drives you autonomously. And at that time, because the vehicle is complete control, you can actually go to sleep. And if you're sleeping when you come close to the destination, it'll park you, and you wake up and drive when you're ready to take it. Yeah. And you get charged by the mile. And that's the key point. So because autonomy does not have, I don't want to be driven autonomously every time. I want to be driven autonomously only under some conditions. I value autonomy only under some circumstances, and the value of autonomy for me is different, and therefore, ideally, I would like to pay only for the autonomy when I really need it. I don't want to pay for all my sensors and costs up front. Here is an opportunity where I pay for my autonomy as a service. I pay by the number of miles that I travel autonomously. So this, I think, provides an opportunity for monetization of autonomy, and this certainly allows private infrastructure players to come into this space. Yeah? So because there's going to be tremendous investment costs associated with instrumenting roadside units every 50 to 100 meters with sensors and having connectivity. Yes, of course. But there is also an opportunity to monetize the usage of that. And that's kind of really the opportunity that we want to present and talk about. So it's not only technical value proposition, so there's a value proposition for a large ecosystem. We believe the automotive OEMs will be only happy because they don't have to deal with taking on additional liability while they still remain in the space of autonomous vehicles. Private infrastructure operators, toll booth operators, cell phone operators, cell tower companies, lighting and urban infrastructure companies, a whole slew of companies suddenly get an opportunity to participate in this autonomous ecosystem. Device makers, the people who make the sensors, the people who make the integration of the sensors that go onto the roadside units, opportunities for them. And the application makers. So when you have a smart connect that carries a whole bunch of information, the number of applications that you can have is limited only by imagination. I believe that there will be a whole slew of people who will be making different types of applications, leveraging the information that comes in while you're driving. And of course, law enforcement, infrastructure maintenance, traffic management, a variety of users can easily be seen. And of course, society at large, because we believe that this would actually accelerate the penetration of autonomous vehicles, at least in specific corridors. So on a corridor by corridor basis, you can dramatically improve the penetration of autonomous vehicles, thereby reaping the quote unquote promised benefits of autonomy. So that's kind of where I want to start. I mean, there are many open research questions, and we don't have anything solved. Yeah, I mean, we have ideas, and we know the problems exist. We are working on them, but really, there's a lot of work still that remains to be done. We have demonstrated the core functionality at Texas A&M, but we want to increase the complexity of the scenarios that we will be demonstrating. We want to increase the scope of the what we're doing. We want to go from 450 meters to a 2-mile loop. People are working on resilience with respect to cyber attacks, to communication failure. There are a variety of opportunities for doing research on pricing models, perhaps elastic auction-based pricing models. Dr. Korok is an expert on that. Then there's government-private industry partnership models that needs to be looked at. There are legal, risk, and regulatory environment implications that need to be discussed. A variety of business models. I'm not going to go through all this, and last but not least, the issue of privacy. How do we ensure that in the, having thousands of cameras all around the road does not infringe on people's privacy? So I say with that, that I leave, and I'll pass it on to Dr. Ratnam. This is just, yeah.
Oh, yeah, thank you. I've been a faculty member at Texas A&M for 10 years. So first year at least, when I was I would come to the lecture room, I would start talking, I would go to the board, write equations and all that. So it was an undergraduate class. So after some of the classes, the undergraduate students came to me and said, "Professor, please, you can say whatever you want, just say howdy before you start anything, and we are all good." So I'm going to say howdy and start my presentation. So, okay, I'm going to talk about infrastructure-based advanced driver assist and autonomous systems. We have already heard a lot of presentations about introduction to autonomous vehicles and the IEA concept. I just want to first acknowledge the support by the Safety Transportation Research Center, which is funded by the US Department of Transportation. And also we work closely with researchers from the Texas A&M Transportation Institute, and of course, all these students who are here, Abhishek, Vamsi, and Kenny, who do all the work. We just present, right? I'll just move on to, I think we have heard from the previous presentations at least, that the road infrastructure is going to significantly benefit both advanced driver assist systems, which is what is called as ADAS, and autonomous vehicles. And in particular, I'm going to talk about proof of concept demonstrations of the IEA concept that Dr. Swamy was talking about for different applications first. And then I'm going to talk about the need for common standards. So this is something I think Ken earlier in the keynote speech mentioned, that we need common standards for evaluating autonomous vehicle technologies and taking it forward. So that's something I'm going to talk about. I'm going to mainly focus on lane departure warning systems because that's closely related with infrastructure. So before I move on to the actual slides, I want to give you a sort of intro video on all the testing that we do. So we work on a wide variety of problems from platooning, car platooning, truck platooning, lateral control, vision-based control, and many other things. So this is just a summary of what we have done. So here, this is a promo video, and it's all the frames that you see, the car frames that you see, were all taken when the car was in the autonomous mode. I'm not really a fan of this music, but they said it's a wide, audience, so I just said, okay, why not? Anyway, so what I'm going to talk about is two parts. The first part, I'm going to talk about the roadside camera unit, which we have installed on each of the 4 poles that Dr. Swamy was talking about, and how we use that information for some of the applications. And then we're going to talk about lane markings, which is an integral part of the lane departure warning systems that at least is available in some of the high-end cars. So first, in fact, just to give you an idea, deep learning algorithms have been used, or at least been significantly developed over the last few years, and you can use them to identify objects on the road and you can actually use them to also classify objects into cars, emergency vehicles, police vans, and all kinds of pedestrians and all kinds of things, and you can actually sort of tailor the response based on what kind of vehicles you identify. So this is just a short clip of having some of these deep learning algorithms trained on the data sets that we have, and you can actually classify them into emergency vehicles and police vans and all that. Obviously, if it's a human manually driven car, you would see an emergency vehicle and try to yield to that vehicle and stop or take the appropriate action. You can also try to emulate that using an autonomous vehicle, and in fact, that's what we have done here. So this is essentially a roadside unit. Here you have two cars in this demonstration. You have the front car, which is an autonomous car, and you have another car that is following, which is an emergency vehicle. So the autonomous car either does not have the sensor to actually know that there is an emergency vehicle behind, or it's just that, just like anything else that you do, you have sensors, but it's just broken, right? It just doesn't work. So in this case, at least what we have is the information from the emergency vehicle is sensed by the camera unit, and then that information is sent back to the autonomous car using the DSRC communication system in real time, and you do the appropriate response. So that's the video here that you're going to see here, and this is all real-time processing. I can go into more details if anyone is interested, but this is for really two vehicles. We also try to do a platoon of vehicles. In fact, we have we have a platoon of 3 cars here. In this demo, actually, we have the front vehicle is autonomous car, the vehicle in the middle is a human-driven car, and the last vehicle, which is basically either it's an emergency vehicle or police van or whatever it is. And here you see that there is no direct line of sight between the autonomous car and the emergency vehicle. And so these are the kind of applications where the infrastructure roadside units, the cameras could really help. So again, the idea, the concept is the same. So the information is, this information is identified by the camera units and then sent back to the autonomous car, which is what is processed in real time. And that's the response that you see here, where essentially the autonomous car comes to the other lane, and of course a manually driven car also parks itself, and you let the emergency vehicle go, right? So these are some of the kind of things you could do. You could also, we have also done that with different test cases. Here we have, modeling humans is always, the most challenging thing to do, and you obviously don't want to test these kind of things using real humans. So we have these human-like robots which you can manually control. You can get them onto the lane and off the lane and all that. So the concept again is the same. The information is basically sent from the camera back to the car using the DSRC unit, and you can actually pose a lot of problems. And I know that Dr. Swamy is working on different applications on this. So this is just an introduction to what is possible when infrastructure is not involved. I think the point, again, I want to emphasize is that I don't think there is one versus other. I think it has to be collaborative. You need maybe some onboard sensing, because many of the cars that you buy already has its own GPS units. It has IMU sensors, so you can use that information, and you can mix it with what you get from the roadside units and do better things and hopefully improve safety and everything. And that's the point here, right? So it can complement the onboard perception units. The infrastructure can actually provide real-time information that when you don't have direct line of sight, and it provides redundancy. And essentially, most of these applications, I'm sure anyone who works on it knows that things fail, and that's the standard. Rule of thumb is that things are going to fail, and how do you accommodate and react to it is what is important. So if you have more sensors and more redundancy, all the better. So anyway, so that's the first part of my talk. The second part is going to concentrate on lane markings, which is really an integral part of the lane departure warning systems. So, we have done we have taken huge strides in autonomous vehicles in the past decade, and this is going to continue, and we are going to see deployments of these autonomous vehicles in some sections of or some cities in the United States, and things are going to improve probably in some sections of the highways, but we are not, I mean, the autonomous vehicles, at least in my lifetime, I don't see that completely replacing all the human-driven vehicles. And at least over the next 40 years, you're going to have human-driven vehicles also, and they have to coexist with autonomous vehicles if at all we have any penetration. So which means that, at least my assumption is that as long as there are human-driven vehicles on the road, you're going to have lane markings to guide us, right? So if you look at it in 2000, there was less than 1% of all the vehicles, at least, equipped with advanced driver assist systems. Depending on what study you look at, by 2030, 50% of the vehicles are going to be equipped with advanced driver assist systems. And when I say these driver assist systems, they could be adaptive cruise control, automatic braking, lane departure warning systems. It could be tire pressure monitoring systems, things like that. The lane departure warning system is one of the key features that is proposed. And the main reason why it's proposed is because people think, at least many studies have shown, that it can actually improve safety. Now, this is just a report from one of the projects, I think, funded by US DOT, where they show that the lane departure warning systems can actually save, that can potentially reduce hundreds of thousands of crashes every year, and can save a lot of lives, and there are a lot of statistics around it. And anyway, I don't want to go through all those numbers, but the point here is that yes, there is potential for safety benefits, but these systems are not yet used, and there are combination of reasons why they are not yet used. It could be because of lack of good lane markings. It could be because we don't have good algorithms yet, or it could be a lack of common performance standards for evaluating these algorithms. So if you look at a lane departure warning system, it's actually just, I just want to tell you how complex this problem is, because, this is just one feature that I would say this is a near-term technology that's going to be there in the cars. And maybe now it's in the high-end cars, but in the next 15, 20 years, I'm sure it's going to be there, more prevalent in most of the cars. And you can see how difficult the problem is when you also have to rely on infrastructure. Now, if you look at a lane departure warning system or a lane detection system, it really consists of three parts. You have the software, you have the hardware, and you have the infrastructure. The software is really the algorithms. Hardware, if you use a camera. So cameras, the reason why everyone talks about cameras is because it's cheap. The LiDARs, I think someone talked about $60,000. You can hope, you can pray and hope that things, costs come down, but it's going to take time to actually have cars equipped with LiDARs and really good radars, right? Cameras are cheap, and that's the reason why they are integral part of these lane detection systems. And of course, you have the lane markings, which is an integral part of the infrastructure. But you can actually get hundreds and thousands of variants based on what kind of algorithm you pick, what camera you pick, and what kind of lane markings and the infrastructure you have. For example, if you just take off lane markings, they could be made of different types of materials. You can have different striping processes. You could have white followed by black, and you could have white and black just juxtaposed. You could have different payment types. So it doesn't matter how good your lane marking is. If you don't have contrast between your lane markings and the surrounding parts of the road, your departure warning system is not going to find it. So it's a contrast that is very important. And also your lane geometry, your thickness, and everything. You also have different cameras you can pick. And of course, the algorithms, many people have been working on that, and I don't have time. I think I'm almost done, so I have a couple of minutes. But the point here is that, we are not at the end of the story, because the performance does not just depend on the algorithm you pick or the sensor you pick or what lane marking you have. It also depends on the environmental conditions. The edge cases, which is going to really determine, it's not the usual normal cases. The normal cases, you can get 90%, 95% accuracy, which may not be good, but it's still better. But it's the edge cases that's going to really determine how good these vehicles are going to be, or how good these systems are going to be. Now, you can have, direct sun, street lights that could deteriorate your performance. You could have, this is one of the hard cases. You could have sun and reflection from the wet surface, snow. You could have old markings, construction sites, pavements. So really, I don't think the camera is going to solve all these problems. You're going to have multiple sensors and do sensor fusion and really to solve this problem. But the key point here is that we do not know what the optimum performance we could get out of just these cheap cameras is at this point in time, at least. There's a lack of common standard which could help us in keeping track of the different components of the evolution of the different components of the system and how it affects the performance. So that's what really we are working on. We are trying to develop at least an open source platform where we can test the infrastructure side, the algorithms, as well as the hardware and all that. And we are also developing metrics to actually evaluate, rank these systems and do it. Of course, it has benefits to the federal agencies, the US DOTs and the state DOTs, because they can actually answer questions like, do my lane markings in my state actually are they fit for level 2 operation or level 3 autonomous vehicle operation? So you can answer questions, simple but basic questions like that. Obviously it's useful for infrastructure providers because they can actually test the new materials, and algorithm developers, of course, because you get new sets of data you can work with. Anyway, I'll just stop with this. I'm just already running out of time. But the point here is that you need a systems approach. It's not about just developing algorithms, or it's not about the infrastructure companies just doing their lane marking. It's an overall system. So you have to look at everything and see if how the improvements in each of the parts will affect the entire system. So with that, I'll just stop. Thank you.
Hi. I'm going to depart from the standard howdy. So anyway, I have about 10 minutes, so I'll try to make it crisp and short and also answer some of the questions that were raised earlier. It's in connection with whatever I've been doing. So I'll focus on certain aspects of connectivity and infrastructure. So for me, infrastructure comes through connectivity, through communications. So what I have been doing for 30 years depends primarily, it's mostly based on how information amongst vehicles will help promote safety and mobility. So this is basically what the focus has been on, and I'll talk a little bit about emergency lane change at the end, but I'll take this time to tell you something about one of the questions that was raised about autonomy and connectivity. So my interest in this particular area of autonomous vehicles goes back to my doctoral thesis, which is about developing automatic vehicle following control algorithms in the 90s for the Automated Highway Systems project. So I'm also interested in the overall, not just in developing the technology, but also assessing what the impact is on traffic safety and traffic mobility. So to give you an answer to that question, so if you're looking at adaptive cruise control systems, which I think all of you know, so the minimum time gap that you need to maintain, okay, which again goes back to my thesis, is that it should be at least twice the sum of all the reaction delays that you would have, reaction lags and delays that you have in the system. Otherwise, you would have these slinky type instabilities, accordion type effect, which will cause pileups. So recently, so this roughly translates to, for trucks, it's about 0.6 to 0.7 seconds. So you're looking at a minimum time gap of about 1.4 seconds. But for eco-platooning and other kinds of things, people are interested in a sweet spot about 0.6 7 seconds, if I'm not mistaken. So to cut down that much with adaptive cruise control systems, it's just not possible. And people have been doing experiments, and especially in the TNO group as well as in the California Path group. They showed that if you had the cooperative adaptive cruise control system, that is like if you had the information of the vehicle ahead, acceleration information of the vehicle ahead, you can cut down the time headway. So in fact, my recent paper, this is a paper that I'm quoting, it basically shows that you can cut it down by a factor of 2 if I had the vehicle acceleration information of the vehicle ahead. But if I had the information of our vehicles ahead, like let's say 3 vehicles ahead, I can cut down this minimum time gap by a factor of 4. So that means that connectivity does help, and here is where the infrastructure can actually play a significant role. For example, this is under the assumption that you have perfect communication, okay? So vehicle-to-vehicle communication will not help in the imperfect case because it's primarily local, because it's autonomy is based on onboard sensors. But if you have connectivity, you can get it through the infrastructure, what's happening much farther ahead. And that is what is required, and that's the reason, that's the way how we can actually make the benefits quantifiable. So, and the same thing with safety also. I mean, there are a lot of safety studies that one can talk about. I also work on, the infrastructure also plays a significant role in commercial vehicle operations. For example, one of the projects that I'm doing with Safety Center, University Transportation Center, is on developing automatic diagnostic systems for autonomous trucks, and essentially the purpose is to facilitate pre-trip inspections, automate them, and you could also use it for automating enforcement inspections and to make sure that trucks comply with the FMVSS 121 standard. So this is the kind of a thing that we're doing. There is some work that infrastructure can also help in traffic harmonization, some work that I've done recently. And then in this particular work, for lack of time, I'll just basically focus on emergency lane change. So how does infrastructure help in emergency lane change maneuvers? I think as the previous speakers, of both my colleagues here and the Florida speakers have mentioned, that you could get real-time information about about vehicles, obstacles in a time-efficient manner. But more importantly, it's the not just that you require for safety, you'd also require some way to localize your position very effectively. And here is where infrastructure can actually play a significant role. So not only in terms of safety, I also want to mention here, there are the two types of queues that you would have for lane change maneuvers. Here, in the first one, you would have the queue for emergency lane change maneuver comes from the front of the string of vehicles if you have. And in the second case, as my colleague has mentioned, if it's like a ambulance or something, it actually comes from the back of the string. So if you had information about these things much earlier, then you could plan and act accordingly. And in the second case, it's even more important because it could save lives. So that's the reason why it's fairly important. So in the emergency lane change maneuver, essentially it's a maneuver in which you have an obstacle in the road, and the vehicles are basically trying to evade this. And here I've shown a 2-lane scenario where the obstacle is in the right lane, and the vehicles are basically trying to move over to the left lane. Okay. The point of this entire exercise is to show that if you did not have the information of the obstacle and there's no communication between vehicles, then the following distance that each vehicle should maintain should be much more than otherwise. The reason is the vehicle behind would be blinded by the vehicle ahead because it will be blocking the obstacle. And there's no, the thing is, you would want the following vehicle to see the obstacle at least at the same location that the preceding vehicle would have seen it. Okay, and this cannot be possible unless you had some sort of communication, or you keep a huge following distance, and that's basically the point of it. So the rough calculations will tell you that it should be at least at the conservative end, it should be about 1.8 seconds of time gap that they need to maintain, and that's clearly not acceptable from the mobility point of view. So I think I don't want to talk a whole lot about the experimental facility at Realis, because I think you've seen this before. So here what we are doing is we are looking at an emergency lane change maneuver design and a controller design. So the difference between regular lane change maneuvers and emergency lane change maneuvers is that the vehicle, when it makes a lane change maneuver, you cannot make use of the lane markings or any of those things, because the trajectory of the vehicle ahead is designed in real time, and what the following vehicle has is only limited preview information about how much ever it is. So the question is whether you can actually make that design happen and have a controller which actually tracks the path of the vehicle ahead. This is essentially what the problem is. So we simulate it, because I'm only dealing with one vehicle from the point of view of safety first, and then after that, probably in the next year or two, we'll do the 2-vehicle and 3-vehicle lane change maneuver demonstration in a similar setting. So in the first run, what you would have is we just had these cones, and then we had the vehicle drive manually. We stored the GPS information, and this GPS information will basically define the trajectory for the second run, which is the autonomous mode. It's as if it's a following vehicle. And what we want to do is we want to track this. And the amount of information that is available to the following vehicle is just a few samples of where it is. That's about all that you have. And you can actually simulate it for multiple vehicles too, because you can store the second vehicle run and then use the first 2 vehicles, and then you can see what happens to the third vehicle. So these are technical details. I'll just skip it. And this is based on the work of my student, which we published which we presented in ECC in Naples. So I have only 1 second left. So I'll just show some demonstrations. What happened? This doesn't work or what? I thought. So this is at 45 miles per hour. I'll just show two videos. This is the aerial view at 45 miles per hour, and the other one will be at 70 miles per hour. So the cones are the ones which are defining what the lane is, that is the double lane change maneuver. This is the in-car view at 45 miles per hour. None of the cones fell away. Okay, this is at 45 miles per hour. So I'll also show you the 70 miles per hour videos, and then I'll stop after that. I'll take any questions. So the drone that we have was not able to keep track of it. So that's why you'll see a block, because this is going too fast. Okay, and this is the last video. This is the other video. This is at 70 miles per hour. So I think I'll just pass the other demo. So thank you, and I'll be glad to take any questions.
Thank you for the interesting presentations. I like the way you emphasize both the opt-in sort of paradigm as well as thinking in systems. A question I had was, so in my Chrysler Pacifica, I have all the latest advanced safety features you described with adaptive cruise control, and I've got Android Auto that's pulling in the data feed from Google with speed limits, congestion, other things. But currently those two systems don't talk to each other, so I'd like to just take the speed limit feed from Google and tell my adaptive cruise control, just go the speed limit that you know is there. Do you see that kind of like system connection emerging in the coming years, or are there different incentives for the OEMs and the data providers that is kind of hindering that, or what do you see as how that might play out? Because then you could have adaptive speed limits if the weather's bad, and that would feed into the adaptive cruise control. How do you see that evolving in the coming years? Thank you.
This is a problem that is considered, this is traffic harmonization. So this is traffic harmonization problem. That's what people usually refer to, where you have, it's like variables or speed things and different sections of the highway where you advise that's the kind of a thing that is considered in traffic harmonization problem. I think this can be done. It's not, as the question is, how do you set the speed limits on the highway depending on the weather conditions? And there is research that is going on, and there's some preliminary work that I had done last year with some of my colleagues. So it can be done.
I just want to add one thing. One is the technologically whether it can be done, and that's of course like what Dr. Darba was saying. It's definitely feasible, but the bigger question is, will the OEM trust the data? And if the data is going to come from a completely different source, then the question of trustworthiness of the data becomes an issue. Whereas if there's a prior agreement that with the infrastructure information provider that this information is trustworthy in some sense, then I think it'll happen. Until then, you cannot do it and make people rely on that.
So normally in scholarly work, we begin with a literature review. Now, in this area, this is quite difficult because you've got a lot of players. There are many universities in this country and all over the world that are working on autonomous vehicle problems. There are many technology companies and auto companies working on this. And even governments are working on all these problems. And I think it really would help this presentation if you step back and gave us an overview, really, that this is a cooperative and competitive effort. Because what you've got, it's in the weeds. You're one player. Maybe you'll be around in 10 years, maybe you won't. And I've seen these presentations, and what I've seen is much more sophisticated than what you've got, but they had a lot more time to present it. And my point is it's useful to put this stuff in context. In other words, what is distinctive about what you're doing as compared with the big picture, which everybody is doing? But this is, as I said, this is a global, cooperative, and competitive effort. But at the same time, those features are what are so important to actually giving us optimism that we're going to get these things sooner rather than later. You may not be part of it, but Stanford might be, Ohio State might be, Michigan might be, or no universities at all. That is all driven by the private sector. So I think broader perspectives on really what's involved here, and not just one small thing and one small problem. You mentioned environmental problems. There are tons of companies who've identified and are working on all these problems as we speak. You know, it's not that you can continue to point to things. I mean, everyone's out there doing this, and I think it's important to really get that message across.
I think it's a fair point, but let me explain 2 points, 2 parts to it.
Number one, most of the work that's being done is either looking at autonomy by itself, focusing on the ability for autonomous vehicles, or using the infrastructure to provide augmented information, such as in traffic intersections and specific places like that. There has not been work that we know of that is focusing on providing real-time information from the infrastructure that will actually be used to drive the vehicle autonomously without using sensors on board the vehicles. So that's actually, we have done the research, and we have not seen any work that does that, number one. Number two, on the point of the environment, the people have recognized that there is an environmental issue. People have been working on different types of snow weather conditions. But what's not happened is taking a systems view and saying we need to have a standardization that will provide a metric that can be used to say, is this lane keep system good? Is this infrastructure that we provide, is the lane marking going to provide adequate support for lane keep assist? Is the camera system going to provide adequate support for lane keep assist? That's the systems level standardization that's not happened. People have been focused on what's important for them. For example, the people who do vision, they're focused on vision algorithms. The people who do the cameras, they are focused on the cameras. But there is not a general purpose effort, and that's understandable. That's kind of what we want to say, and trying to say we would like to have lane keep or lane marking, lane detection standardization, a metric, a reference system that can be used to promote what it means.
I'll just add one more point. At least from my point of view, most of the work that has been done in companies is from the point of view of single vehicle autonomy. That is, you try to have all the sensors on board and try to make your vehicle as safe as possible. I think one of the efforts that we are trying, we didn't have time to present today, but one of the things that we are doing in at Texas A&M is trying to look at safety problems and other issues for a collection of autonomous vehicles when they are connected. So if you have a platoon of vehicles, let's say, driving on the road, and they're all talking with each other, of course, if we have communication, if great communication between the vehicles, it's all good and fine, but what if that doesn't happen? What if there are communication failures? Let's say if you have a collection of 5 vehicles, if there is a communication failure between the first vehicle and the third vehicle and fourth, whatever it is, how does it affect safety and performance? So I think our effort has been focused on that. Companies try to do that. I don't want to name the companies here. They've tried to develop safety metrics from a single vehicle's perspective. But it's all great, but it would not work in reality. The reason is that if you're just looking at single vehicle and just trying to make that safe, I don't think you will get the efficiency benefits that you desire. So if you want safety and if you want to have the kind of performance that people are talking about, then you need to look at the collection of vehicles, and that's the effort that we are looking at. And I don't think the companies are. Those are all long-term problems, research questions, and companies they may get into it, but not right now.
Yeah, don't want to jump the queue, but thanks. So Rick Eddies from Cornell Public Policy. And I want to go to a point Professor Gopalswamy, I have it right, is touched on, which is super important in the policy aspect of infrastructure. And that is, you mentioned charging by the mile. And one of the biggest challenges, seems simple, is how you pay for the infrastructure. And currently we pay on basically a per gallon fossil fuel tax on either gasoline or diesel fuel at both the state and federal level to pay, for the vast majority of the roads. But you mentioned charging by the mile, and the state of Oregon is the leader in pilot projects over the past decade to try to make that simple switch from charging per gallon to charging per mile. And it's been a real slog, a real challenge politically to get drivers to accept that, although the state of California is interested in doing that. So here's my question for anyone on the panel. Do you see the advent of autonomous vehicles as facilitating the acceptance, and they call them mileage-based user fees, MBUFs, and away from a per-gallon gas tax, so that people will be more accepting of incorporating what we would think of in utility pricing as a facility charge into the price of a trip, right? So it's been sort of driver resistance to that seemingly simple change, which is super important in the economics of this. Could we see the interaction of autonomous vehicles and the way you pay for the infrastructure as facilitating that improvement?
Yeah, my thinking is yes. And the reason I say that is if I look at toll roads, that's a prime example where for example, in Texas, we have all these, in fact, a lot of places, we have this auto charging of the tolls. And it's become now so ubiquitous that you start forgetting, and then you start not worrying about it too much, as long as it seems reasonable, and it is actually in some ways based on usage. And so my point is, people would be more comfortable with paying by mile if the process of doing it is very easy and very convenient. If it's seamless for them, they almost don't have to worry about it. Then I think it will be okay, as against if you have to actually pay explicitly for a bill. Yes.
Great, thank you. Well, first of all, I wanted to build off Cliff Winston's question. And I think, first of all, I think it's not true that there are no companies that are working on infrastructure-dependent autonomy. I'm aware of 2 companies that are building their sensors into the infrastructure because their use cases, they want to serve a limited service area of multiple vehicles, so it turns out to be more effective to build the sensors into the infrastructure than building the sensors into each vehicle. So I think, and so I'm aware of 2 companies who are building out that approach in commercial service. And so I think that gets to a larger question is, what is the right mechanism for public-private interaction and particularly private academic interaction? And I think this is what I'd like to turn this into a question. And the question is, what is your mode of interaction with the private sector been over the last 5 years, in which we've seen not just 1, but 2 sea changes in the direction of investment in autonomous vehicles? About 5 years ago, we started to see a massive amount of private sector investment in autonomous vehicles. Brookings put out a report that said about $80 billion had been spent on JVs and M&A in the autonomous vehicle space. And then last year or so, we're seeing increasing consolidation and engagement in the academic sector. So I would hope that the approach around how do you divide problems, which ones are best approached by the public sector and which are best approached by an academic sector and which ones are best approached by the private sector has changed. So I'm curious about what you've seen over the last 5 years or so.
It's a pretty complicated question. So let me try to answer that. My thinking is that, first of all, some of the work that's done by private companies, we don't have access to that. All we know is their marketing blurb. So from a literature survey perspective, we will not be able to assess what exactly they are doing. And so that's my answer was more in the context of the universities. So that's number one. Number 2, but on the flip side, there have been companies, you're right. For example, I think Daimler has a parking lot scenario where you actually drive inside a parking lot where there's a whole bunch of sensors embedded in the infrastructure that support that. What we have been working on is the extreme scenario where we are saying, okay, how much can you push it? Can you be completely independent from sensors to be on the vehicle and use almost 90% of the information coming from the infrastructure? That's kind of how we have been trying to position ourselves. In terms of the public-private partnership, it's actually a ongoing thing. For example, we are discussing with some companies, companies which do lighting, for example, who want to get into smart infrastructure, smart cities. They have been willing to support it. In fact, we may even actually have a formal agreement with them to support some of the work. We have had conversations with many other companies, such as 5G companies that want to install 5G because they need a physical infrastructure also, and we have the Release campus, and so they've been willing to come down and say, okay, we will install 5G. Can you demonstrate use of that in a very meaningful application? So that's something that we are working on. We have talked with automotive OEMs. They have expressed interest, but we have not had a direct conversation, actual work yet. Yeah, that's kind of, yeah.
I just want to make a fundamental comment about basic research and investment in basic research. All of you sitting there, 30 years ago, the investment at Berkeley and other places in intelligent control system, path planning, computational geometry, the whole path program at Berkeley. So I think we have to very much pay attention to the fact that investment in those basic ideas, risky ideas 30, 40 years ago that took place is now paying off. And you people are talking about just certain aspects of it, but the basic investment was made 30, 40 years ago, and we should try to keep, as a policy matter, in perspective that fact. Because in the present environment, you will see that we are only picking up the fruits, but we are not looking at the roots of the thing. I think we have to pay attention to that fact.
Yeah, in fact, I'm one of the early graduates of the PATH program. So I was there with PATH from 19. That was what my PhD program was on. So it's thanks for pointing that out. People seem to have forgotten the PATH program and its impact.
I also work for PATH, and we work on fundamental problems, and that's where my interests are. Today's presentation is just one slide. I had 15 minutes to talk, so if you give me more time, I can talk about the fundamental problems. I'm not sure how much of the audience I can retain, but I'll be happy to talk about it.
Thank you.
And there's lunch right outside of the auditorium for all of participants.